Meteorology is a core subject in aviation, underpinning safe and efficient flight operations. In this comprehensive overview, we will cover the entire theoretical syllabus of EASA ATPL Meteorology. The viewer will learn about the structure and properties of the atmosphere, the dynamics of wind and global circulation, atmospheric thermodynamics, cloud formation, precipitation processes, and the behavior of air masses and fronts. We will examine pressure systems from benign anticyclones to violent tropical storms, as well as climatology patterns across different regions. Disclaimer: all sections are shown below, so feel free to jump between them. All sources used are in the description below. The video is not intended to be visually accurate. The priority is on the information provided. Happy studies. Critical flight hazards, including icing, turbulence, wind shear, thunderstorms, and other weather threats, will be discussed in detail. Finally, we will outline how meteorological information is observed, charted, and used in flight planning and the services that provide these vital data. This structured lesson is intended to match EASA standards, delivered in a clear, professional tone, suitable for airline pilot training. The atmosphere. Overview. The atmosphere is the envelope of gases surrounding Earth, extending from the surface into space. It provides the medium for weather and flight, and its properties vary with height. In this section, we discuss the atmosphere's composition, vertical divisions, and fundamental properties such as temperature, pressure, and density. We also introduce the International Standard Atmosphere, ISA, as a reference model, and explain altimetry, the principles by which pilots measure altitude using atmospheric pressure. Composition, extent, vertical division. The Earth's atmosphere consists primarily of nitrogen and oxygen, with trace gases and varying water vapor. Dry air by volume is about 78% nitrogen and 21% oxygen, with roughly 1% argon and other trace gases, including carbon dioxide. Water vapor is also present in variable amounts, on average around 1% at sea level, higher in humid tropics and near zero in cold, dry regions. Though a minor constituent by percentage, water vapor is meteorologically significant as it leads to cloud formation and precipitation. The atmosphere has no sharp physical boundary, but gradually thins with altitude. About 3/4 of the atmospheric mass lies within the lowest 11 km. For descriptive purposes, we divide the atmosphere into vertical layers defined by temperature characteristics. Troposphere, the lowest layer extending from the surface to an average height of about 8 to 18 kilometers depending on latitude and season, highest over the equator, lowest over the poles. Nearly all weather phenomena occur in the troposphere, which contains about 99% of the atmospheric water vapor. Temperature generally decreases with height in this layer at a rate called the environmental lapse rate. Tropopause, the boundary at the top of the troposphere, marked by a cease of temperature drop. Its altitude varies, around 17 kilometers in tropics, 11 kilometers in mid-latitudes, and as low as 7 to 10 kilometers in polar regions. The tropopause caps most cloud growth. Above it, convective weather is limited. Stratosphere, above the tropopause, extending roughly up to 50 kilometers. Here, temperature increases with height due to ozone absorption of solar radiation, creating a stable temperature inversion. The stratosphere is very dry, with little weather, aside from rare nacreous clouds in the lower stratosphere. Jet aircraft often cruise near the tropopause or lower stratosphere to avoid weather and benefit from smoother air. Higher layers exist above 50 kilometers, but these have negligible relevance for standard aviation operations, aside from effects on long-range radio or spacecraft. Virtually all practical aviation weather concerns are confined to the troposphere and lower stratosphere. Air temperature. Air temperature is the measure of the thermal energy of the atmosphere. It determines atmospheric stability and the vertical motion of air. Temperature is measured in degrees Celsius, (degC), for aviation in EASA regions, with Kelvin used in scientific context. At sea level in temperate regions, typical surface air temperatures vary diurnally and seasonally, but a baseline reference is provided by the EASA 15 degree at mean sea level. In the troposphere, temperature generally decreases with altitude. The average vertical temperature gradient or lapse rate is about 6.5 degrees per 1,000 lassos, approximately 2 degrees per 1,000 feet in the lower atmosphere. However, actual lapse rates vary. When the lapse rate is steep, air cooling rapidly with height, the atmosphere is potentially unstable. When it's shallow or temperature increases with height, inversion, the atmosphere is stable. Near the ground, temperature is influenced by surface heating and cooling. During the day, solar radiation warms the surface and the air above it, while at night, the surface cools by radiation, cooling the air in contact with it. This diurnal cycle causes a surface inversion on clear, calm nights and a well-mixed warm layer near the ground in daytime. Temperature distribution is also affected by latitude, solar angle, and seasons. Equatorial regions are warm year-round, whereas higher latitudes see large seasonal swings. Temperature differences drive atmospheric circulation on both global and local scales. Importantly for pilots, temperature deviations from EASA can affect aircraft performance and altimeter readings. Cold air being denser causes true altitude to be lower than indicated, if not corrected. Atmospheric pressure. Atmospheric pressure is the force per unit area exerted by the weight of the air above. At sea level, the standard pressure is defined as 1013.25 HPA, hectopascals, equivalent to 1 atm, or 29.92 inches of mercury. Pressure decreases with altitude because there is less air above. Near the surface, pressure decreases roughly by 100 HPA per 30 feet of ascent in the lower levels. Though this rate is not constant and diminishes at higher altitudes as air density decreases exponentially. Pressure varies horizontally as well, forming high-pressure areas, anticyclones, and low-pressure areas, depressions. These pressure differences drive wind and weather systems. Isobars on weather charts connect points of equal sea level pressure and help identify pressure systems and gradients. In the vertical, pressure drops from around 1013 HPA at sea level to about 226 HPA at 11 kilometers, the standard tropopause level. Because aircraft altimeters measure static pressure to infer altitude, variations in pressure have direct operational implications. Pilots must adjust altimeter settings to the current sea level pressure, QNH, for accurate altitude indications when flying at lower levels. If flying from a high pressure into a low pressure area without resetting the altimeter, the aircraft will be lower than the altimeter indicates. High to low, look out below, underscoring the importance of correct pressure settings for terrain clearance. Air density. Air density is the mass of air per unit volume, which decreases with altitude, temperature increase, or humidity increase. At sea level under EASA conditions, air density is about 225 kg. Density is governed by the gas law, T, for a given composition, meaning density is proportional to pressure and inversely proportional to temperature in Kelvin. Thus, air becomes less dense, thinner at higher altitudes, lower pressure, or when it is warmer. Humid air is slightly less dense than dry air at the same temperature and pressure because water vapor, H2O, is lighter than the nitrogen-oxygen mixture it displaces. For pilots, density is critical. Engine power, lift, and propeller thrust all decrease in less dense air. Density altitude is a term for the equivalent altitude in the EASA that would have the same air density as the current conditions. It increases on hot or high elevation days, degrading aircraft performance. Although density itself is not directly measured in routine weather reports, pilots infer it from pressure, temperature, and humidity. In summary, lower pressure, higher temperature, and higher humidity each reduce density, which can adversely affect climb rates and engine output. International Standard Atmosphere, ISA. The International Standard Atmosphere is a reference model that defines average atmospheric properties by height under standard conditions. ISA sea level conditions are set at a pressure of 113.25 HPA, temperature of plus 15 degrees, and density of 1.225 kg through. The standard lapse rate in the troposphere is defined as a temperature decrease of 6.5 degrees per 1,000 met, approximately 0.98 degrees C per 1,000 foot, up to the tropopause. The ISA tropopause is assumed at 11 kilometers, 36,090 feet, with a temperature of 56.5 degrees, and the temperature is taken to remain constant at 56.5 degrees C through the lower stratosphere above that altitude. The ISA provides a common baseline for aircraft performance calculations and altimetry. Engines, aerodynamics, and altimeters are often calibrated assuming ISA conditions, and performance tables use EASA deviations. Pilots and dispatchers refer to EASA plus 10, for example, to mean a temperature 10 degrees above standard for that altitude, which indicates less dense air and potentially reduced performance. When actual conditions differ from EASA, which is almost always, corrections are applied. For instance, if the air is colder than EASA, true altitude will be lower than indicated for a given pressure level, a concern for high-altitude terrain clearance in very cold air. Altimetry. Altimetry is the measurement of altitude using atmospheric pressure. An altimeter is essentially a sensitive barometer calibrated to display altitude in feet or meters rather than pressure. It assumes the ISA pressure lapse rate. Hence, in standard atmosphere conditions, the altimeter will read true altitude. However, when pressure or temperature deviate from standard, errors arise if not accounted for. Altimeter settings. To ensure altimeters read correctly at takeoff, en route and landing, pilots use altimeter subscale settings. QNH. The pressure setting that causes the altimeter to read altitude above mean sea level for a given location. When an aircraft is on the ground at an airfield and the altimeter is set to the current QNH, it will indicate the elevation of that airfield. QFE, the pressure at the airfield elevation, station pressure. If the altimeter is set to QFE, it will read 0 on that field, or height above that specific datum if airborne nearby. QFE is sometimes used in military or older procedures for circuits, but QNH is the primary reference in civilian aviation. Standard setting, QNE, 1013 HPA, 29.92 in HG, used when flying at standard flight levels, usually above the transition altitude. At this setting, altitudes are referred to as flight levels, FL. For example, FL 350 corresponds to the pressure level that would read 35,000 pound-foot on 1013 HPA. Pilots transition from QNH to standard setting when climbing through the transition altitude and revert to QNH when descending through the transition level, to ensure vertical separation and terrain clearance using a common reference. Altimeter errors and corrections. If flying from a region of higher pressure to lower pressure without resetting QNH, the altimeter will overread, indicate higher than actual, and the aircraft will be lower than indicated. Conversely, flying into higher pressure than set will cause underreading. Temperature deviations also matter. In colder than standard air, true altitude is lower than indicated for a given pressure level, which is why in extreme cold conditions, altitude corrections are applied when flying a procedure over high terrain. Most aviation authorities publish tables for altitude correction in cold weather. Another consideration is mountainous terrain pressure anomalies. Strong winds across mountains can create a localized low pressure on the lee side and near mountaintops due to the Venturi effect of accelerated airflow. This can cause an altimeter to overread, meaning the aircraft is actually lower than the altimeter indicates when flying near mountain ridges in high winds. Pilots therefore add extra altitude margins in such conditions. Overall, accurate altimetry through proper setting and understanding of atmospheric effects is crucial for safe vertical navigation. Wind, this is the movement of air relative to the Earth's surface. Wind arises from pressure differences in the atmosphere and is modified by the effects of Earth's rotation and surface friction. Understanding wind is essential for pilots. It affects takeoff and landing performance, navigation, and the formation of weather systems. In this section, we define wind and how it is measured, examine the fundamental causes of wind, including pressure gradients and Coriolis force, survey the global circulation patterns, and explore local effects. Definition and measurement of wind. Wind is defined as air in motion relative to the Earth's surface. By convention, wind direction is reported as the direction from which the wind blows. For example, a north wind blows from north towards south. Wind speed is commonly measured in knots for aviation use or meters per second in meteorological reports, and direction in degrees true, often rounded to the nearest 10 degrees in observations. Wind at the surface is measured by anemometers for speed and wind vanes for direction, typically at a standard height of 10 meters above ground in an open exposure. Pilots receive surface wind information from METAR reports and control tower updates, which give mean wind direction and speed, often with gusts if significant. Aloft, winds are measured by weather balloons, radio sondes tracking drift, Doppler radar wind profilers, and aircraft reports. Winds at cruising altitudes are forecast in flight documents and depicted on upper wind charts. In flight, pilots infer wind by the tracking versus heading differences and via inertial or GPS calculations. Importantly, wind is rarely constant. It varies in time and space. Thus, reports often include a mean wind and a variability range. For example, a METAR might state 210 dig 15 G25, meaning wind from 210 dig at 15 knots, gusting 25 knots. Understanding wind measurements and terminology allows pilots to anticipate drift, crosswind components for landing, and potential turbulence or shear. Primary cause of wind. The primary cause of wind is horizontal pressure difference. Air moves from high-pressure areas toward low-pressure areas under the influence of the pressure gradient force. If Earth did not rotate and had a uniform surface, air would flow directly from highs to lows. However, the rotation of the Earth introduces the Coriolis effect, which deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection causes winds to turn and flow roughly parallel to isobars at altitude, rather than directly across them. Around curved isobars, the centrifugal force also plays a role, leading to gradient wind, which accounts for the curvature. Around a high anticyclone in the northern hemisphere, the wind flows clockwise, anticyclonically, and slightly outward. Around a low cyclone, it flows counterclockwise, cyclonically, and slightly inward. The angle at which wind crosses isobars toward lower pressure is small at altitude, geostrophic flow, but near the surface, friction slows the wind and reduces Coriolis deflection, causing winds to blow at an angle across isobars. Thus, the primary cause of wind is the pressure difference, pressure gradient, generated by unequal heating of the Earth's surface and other factors, and its direction and speed are shaped by Coriolis force and friction. Convergence, air flowing into a low, causes upward motion, while divergence, air spreading out from a high, causes subsidence. These vertical motions are tied to cloud formation or clear weather, linking wind to broader weather processes. General global circulation. On a global scale, differential heating between the equator and poles drives a general circulation composed of several large convective cells. The idealized three-cell model of Earth's atmospheric circulation is as follows. Hadley cell, 30 degrees latitude. Strong solar heating at the equator causes air to rise in a band of low pressure and convergence called the Intertropical Convergence Zone, ITCZ. This rising air reaches the tropopause, spreads poleward, and descends around 30 degrees in subtropical high-pressure belts. From these highs, some air returns to the equator at low levels as the trade winds, which blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere toward the ITCZ. The Coriolis effect deflects these equatorward winds westward, hence the easterly trade winds. Ferrule cell, 30 to 60 degree latitude. In mid-latitudes, the circulation is less thermally direct. The ferrule cell is a secondary circulation where surface winds flow poleward from the subtropical highs towards subpolar lows around 60 degrees in latitude. These prevailing westerlies, southwesterly winds in the northern hemisphere, northwesterly in the southern hemisphere, arise from air moving poleward and eastward due to Coriolis deflection. The westerlies and transient low-pressure systems, extratropical cyclones, dominate mid-latitude weather, transporting warm air poleward and cold air equatorward. Polar cell, 60 to 90 to latitude. At the poles, cold, dense air creates persistent high pressure. Air subsides over the poles and flows outward towards 60 degrees as cold surface winds, easterly in both hemispheres due to Coriolis turning them westward. Around 60 degrees, this cold air meets warmer air from lower latitudes along the polar front, forcing air to rise and completing a weak polar cell circulation. These 3 cells per hemisphere are a simplified model. In reality, the distribution of land and sea, seasonal changes, and the rotation, Coriolis, produce semi-permanent pressure systems like the equatorial low, subtropical high-pressure ridges, e.g. the Azores high, subpolar lows, e.g. the Icelandic low, and polar highs. The general circulation explains phenomena such as the trade winds in the tropics, the westerlies in the mid-latitudes, and the jet streams, which form near the boundaries of these circulation cells. It also leads to climate zones, for instance, rising motion and heavy rainfall near the equator, and sinking air with arid climates near 30-degree desert belts, etc. For pilots on long-haul flights, understanding global wind patterns like tailwinds in the jet stream or doldrums near the equator can be important for route planning. Local winds. Local winds are mesoscale circulations, usually influenced by terrain, coastlines, or other local differential heating patterns. Some important types of local winds include land and sea breezes. Along coastlines, the daily heating contrast between land and water produces a cyclic breeze. By day, land heats up faster than water, creating lower pressure over land and a pressure gradient from sea to land. A cooling sea breeze that often begins by late morning and can strengthen through afternoon, bringing cooler marine air inland. At night, land cools faster, developing higher pressure over land relative to the warmer sea. So the wind reverses as a gentle land breeze blowing from land out to sea during late night to early morning. Valley and mountain breezes. In hilly or mountainous terrain, on a sunny day, the mountain slopes are heated and warm the adjacent air, causing it to rise. This draws air up from the valleys, an upslope anabatic wind or valley breeze that flows up the slopes and valleys during the day. Conversely, at night, the slopes cool by radiation, chilling the air, which then flows downslope into the valleys as a katabatic wind, mountain breeze. These winds are typically light to moderate, but can significantly affect takeoffs and landings at mountain airports, and they can lead to upslope cloud and fog formation in the afternoon, or frost pockets at valley floors at night. Fuan wind, warm downslope wind. When stable air is forced over a mountain range, the descending air on the lee side warms and dries out, often leading to a strong, gusty warm wind downhill. This föhn effect, known by local names such as Föhn in the Alps, Chinook in the Rockies, Zonda in the Andes, occurs after moisture has been precipitated out on the windward side. The leeward air, now dry, warms at the dry adiabatic lapse rate as it descends, so it arrives on the valley floor significantly warmer and drier than it was on the windward side at the same elevation. Winds can rapidly raise temperatures, melt snow, and cause turbulence and wind shear. They often bring clear skies to the lee side, a rain shadow, while the windward side remains cloudy and wet. Other regional winds. Various regions have named local winds caused by particular setups. For example, the Mistral is a cold northwesterly wind that funnels down the Rhône Valley in France on clear, dry days due to high pressure over Europe and low pressure in the Mediterranean. The Bora in the Adriatic is a cold, strong wind descending to the coast from the northeast, from the Balkans. The Scirocco is a warm, humid southerly from the Sahara that brings dust to southern Europe. While the specifics differ, pilots must be aware that local wind systems can cause sudden changes in wind direction and strength, affecting turbulence and aircraft performance. Mountain waves, standing waves, lee waves. Mountain waves are a phenomenon that occurs when stable air flows over a mountain range or ridge and oscillates vertically on the lee side. If there is a stable layer above the mountain and winds blow roughly perpendicular to the range, typically at least 15 to 20 knots or more, the conditions are ripe for mountain or lee waves to form downwind of the terrain. These waves are called standing because while the air is moving rapidly through, the wave pattern remains stationary relative to the mountain. In a mountain wave, air is forced upward by the terrain, creating an updraft on the windward side. Then, as it descends on the lee side, it can overshoot its equilibrium and rise again, setting up a wave train that propagates downwind for many tens or even hundreds of kilometers. The crests and troughs of these waves can reach well above the height of the mountains. Strong mountain waves have been known to extend into the lower stratosphere. Mountain waves manifest with distinctive cloud forms. On the crests of waves, if moisture is present, lenticular clouds, lens-shaped stationary clouds, may form and hover in place. Just downwind of the ridge, a cap cloud or fen wall may cling to the mountaintop, and below the first wave crest, a turbulent rotor cloud sometimes forms, indicating a rolling vortex below the wave. Even in clear air, mountain wave turbulence, especially near the rotor and in strong waves, can be severe. For aviators, mountain waves present several hazards: strong vertical currents, updrafts and downdrafts that can exceed thousands of feet per minute, making it difficult to maintain altitude, severe turbulence in and below rotor clouds, and significant altimeter errors. Lee side low pressure can cause altimeters to overread. Pilots should be cautious when flying on the lee side of mountains in strong winds aloft. Clues to mountain waves include lenticular clouds and forecast products like significant weather charts that mark mountain wave activity.
Turbulence. Turbulence is the irregular, disturbed flow of air characterized by eddies and vertical currents. Pilots experience turbulence as bumps or jolts. It can range from light, gentle oscillations, to extreme, throwing an aircraft out of control or causing structural damage if severe. Turbulence has several causes and types. Mechanical turbulence, caused by wind flowing over rough terrain, buildings, or other obstacles, which creates eddies. Near the ground, strong winds interacting with hills, trees, or man-made structures produce low-level turbulence. For example, on a gusty day, the approach to an airport surrounded by buildings or terrain can be turbulent. Thermal, convective, turbulence, caused by buoyant lifting of air due to surface heating. On a hot day, bubbles of warm air rise, thermals, causing bumpiness especially below cloud base. Flying at lower altitudes on sunny afternoons often encounters this thermal turbulence, which is typically moderate in small aircraft over land and can be minimized by flying at times or altitudes where the atmosphere is more stable. Turbulence in cloud, particularly within convective clouds, towering cumulus or cumulonimbus, there are strong updrafts and downdrafts that create severe turbulence. Thunderstorms are especially dangerous, with powerful and chaotic air movements, including downbursts. Frontal turbulence, near frontal zones, especially fast-moving cold fronts, the wind shear and embedded convective elements can produce turbulence. A sharp cold front may have a squall line of thunderstorms or gusty winds causing a rough ride even outside of precipitation. Clear air turbulence, CAT, this occurs in the absence of visible cloud, often associated with wind shear in the upper atmosphere, such as near the jet stream or around mountain wave regions well downstream. CAT often occurs at boundaries of air masses or near jet streaks where there are sharp changes in wind speed or direction. Pilots rely on forecast CAT areas and pilot reports, as CAT cannot be seen on weather radar. Wake turbulence, although not meteorological, it is generated by aircraft. It is worth noting as a turbulence hazard. Wingtip vortices from heavy aircraft can persist and drift with the wind, posing risk to following aircraft. In summary, turbulence can occur at any altitude, from ground level, mechanical and convective turbulence, to cruise levels, CAT. Pilots mitigate turbulence by avoiding known areas, for example, circumnavigating thunderstorms or known mountain wave regions, and by flying at appropriate speeds, at or below maneuvering speed VA, to prevent overstressing the aircraft in turbulence. Passenger safety, seat belts, and securing loose items are also important when turbulence is expected. Modern aircraft are built to withstand significant turbulence, but sustained severe turbulence should be avoided whenever possible. Jet streams. Jet streams are narrow bands of very strong winds found in the upper levels of the troposphere, typically near the tropopause. They are a product of horizontal temperature gradients, most prominently, the polar front jet forms above the boundary between cold polar air and warmer mid-latitude air, and the subtropical jet forms near 30 degrees latitude due to conservation of momentum where Hadley cell air descends. Jet streams generally flow west to east, westerly winds, in both hemispheres. A typical jet stream is located around 30,000 to 40,000 feet in altitude, 9 to 12 kilometers, though its height and strength vary. Wind speeds in the core of a jet stream often exceed 90 knots and can reach 150 to 200 plus knots in the strongest winter jets. The polar jet meanders around 40 to 60 degrees latitude in each hemisphere, shifting seasonally. The subtropical jet sits around 25 to 35 degrees latitude. For aviation, jet streams are significant for several reasons. Flight planning. Flying in or near a jet stream can greatly affect ground speed. Westbound flights avoid strong headwinds by staying out of core jet flow when possible, whereas eastbound flights may plan to ride a jet stream tailwind to save time and fuel. Clear air turbulence. The shear on the edges of jet streams is a prime cause of CAT. Strong vertical or horizontal wind gradients near a jet core can induce turbulence, especially on the polar side of the jet where the wind speed often falls off sharply. Pilots crossing a jet stream often anticipate turbulence and secure the cabin accordingly. Weather development. Jet streams are associated with the development and steering of weather systems. Areas of divergence aloft near jet streaks can intensify surface lows. While this is meteorological detail beyond operational flying, pilots should note that the presence of a strong jet often coincides with active frontal systems and storm development below. Jet stream positions are depicted on high-level significant weather charts and wind/temperature charts. Pilots operating high-performance aircraft at cruise altitudes pay close attention to forecast jet locations. A common example is North Atlantic flights. Westbound routes may avoid the strong west-east jet core in winter, whereas eastbound flights try to exploit it. Overall, jet streams are a double-edged sword, useful when aligning with one's route, but requiring caution due to turbulence and the need for altitude/route adjustments. Thermodynamics. Overview. Atmospheric thermodynamics deals with heat, energy, and the properties of air, especially as they relate to moisture. In meteorology, thermodynamics explains how water vapor behaves, how clouds form, and why air becomes buoyant or stable. This section covers humidity measures, phase changes of water and associated latent heat, and adiabatic processes, temperature changes in rising or sinking air. These concepts underpin the formation of clouds, fog, and precipitation, and they determine atmospheric stability, crucial for predicting thunderstorms, turbulence, and cloud development. Humidity. Humidity is the amount of water vapor in the air. It can be expressed in various ways: absolute humidity, the mass of water vapor per volume of air, g per cubic meter. This is less commonly used in aviation. Mixing ratio, the mass of water vapor per mass of dry air, typically in grams per kilogram. This measure is conserved when air parcels move vertically without condensation or evaporation. Relative humidity, RH, the ratio, in percent, of the current water vapor amount to the maximum possible at that temperature, saturation point. RH indicates how close the air is to being saturated. At 100% RH, the air is saturated and condensation can occur. Dew point, perhaps the most pilot-friendly measure, it is the temperature to which air must be cooled, at constant pressure, to become saturated. RH 100%. The dew point is always at or below the actual air temperature. A small spread between temperature and dew point, for example, a difference of 1 to 2 degrees Celsius, means the air is nearly saturated, often a precursor to fog, low clouds, or dew. Pilots pay attention to dew point in weather reports. Measures include temperature and dew point, because it helps indicate humidity and the potential for mist or cloud base height. A rule of thumb is that the cloud base of convective clouds is roughly 400 feet per degree Celsius of temperature dew point spread, in temperate climates. Warm air can hold far more water vapor at saturation than cold air. For instance, air at 30 degrees Celsius can contain several times the water vapor of air at 10 degrees Celsius before reaching saturation. This is why humidity is often higher in tropical climates and why cold winter air is very dry. High humidity in the atmosphere can lead to reduced performance, since moist air is less dense and also can contribute to carburetor icing in piston engines under moderate temperatures. But its most critical effect is on weather. Humidity is the fuel for cloud and precipitation formation. Change of state of water. Water is unique in the atmosphere because it can exist in all three phases: vapor, liquid, solid, and transition between them at common atmospheric temperatures. The primary phase changes and their effects are evaporation, liquid water to vapor. This process requires heat absorption, latent heat of evaporation, from the environment. For example, when water evaporates from the ocean or a wet surface, it cools that surface and stores energy in the vapor. Condensation, vapor to liquid water. This releases latent heat to the surrounding air. n.wikipedia.org. Cloud formation is essentially condensation, or deposition, in rising air, and the release of latent heat during condensation warms the air, providing energy that can enhance buoyancy, important in the growth of convective clouds and storms. Sublimation, direct transition from solid, ice, to vapor, which absorbs heat, like evaporation. The reverse, deposition, is vapor turning directly into ice, for example, frost formation or ice crystals in subfreezing clouds, which releases latent heat. Freezing, liquid to solid, releasing latent heat, though usually a smaller factor in atmospheric processes because it often occurs after condensation in clouds, for example, supercooled droplets freezing to form ice. Melting, solid to liquid, absorbing latent heat. Each change of state involves large amounts of energy. For instance, the condensation of water vapor releases about 2.5 times 10 to the power of 6 J per kilogram of water, the latent heat of condensation. This energy release is what powers thunderstorms and hurricanes, as huge quantities of water vapor condense into cloud and rain, heating the air and driving vigorous updrafts. Conversely, evaporation in one area, like the ocean, stores that energy, which can later be unleashed when condensation occurs. In practical terms for pilots, the evaporation of rain as it falls can lead to cooling of air and stronger downdrafts, as in microbursts. Sublimation of snow can cool air masses. And the melting of falling snowflakes can create cooling layers near above freezing surfaces. These processes, while not directly controlled by pilots, shape the thermal structure of the atmosphere that pilots fly in. Adiabatic processes. Adiabatic describes a process in which no heat is exchanged with the environment. In the atmosphere, vertical movements of air are often treated as approximately adiabatic, meaning a rising parcel of air cools due to expansion, as pressure decreases aloft, without exchanging heat with surrounding air, and a sinking parcel warms by compression. The rate at which an unsaturated, no condensation, air parcel cools when lifted is the dry adiabatic lapse rate, DALR, about 9.8 degrees Celsius per 1,000 meters, approximately 3 degrees Celsius per 1,000 feet. This is a constant physics-derived rate for ideal gases. If the air cools to its dew point and becomes saturated, condensation begins. From that level upward, the parcel cools more slowly because the release of latent heat partially offsets the cooling. This slower rate is the saturated, or wet, adiabatic lapse rate, SALR. The SAL is not fixed, it varies with temperature and moisture, roughly 1.5 degrees Celsius per 1,000 feet, 5 degrees Celsius per kilometer, in very warm, humid air to about 2.5 degrees Celsius per 1,000 feet in cold, drier air, and average often cited is around 1.5 degrees Celsius per 1,000 feet for temperate cloud conditions. Understanding these lapse rates is crucial to assessing atmospheric stability. If the environmental lapse rate, the actual decrease of temperature with height in the atmosphere, is greater than the DAL, i.e., air cools very quickly with height, the atmosphere is absolutely unstable, a lifted parcel, even unsaturated, will be warmer than its surroundings and keep rising, leading to convection. If the environmental lapse rate is smaller than the SAL, air cools very slowly with height or even increases with height, the atmosphere is absolutely stable, any lifted parcel will end up cooler, denser, than its environment and sink back down, suppressing vertical motion, often the case in inversions. If the lapse rate is between the DAL and SAL, the atmosphere is conditionally unstable, unsaturated air is stable, but if the air is lifted and becomes saturated, forming cloud, it may become unstable, because the parcel then follows the SAL. This is the common scenario for afternoon thunderstorms. The air near ground is stable early on, but surface heating lifts some air to its lifting condensation level, LCL, where cloud forms and beyond which the parcel, now rising moist adiabatically, finds itself warmer than the environment, if the environment's lapse rate is steep enough aloft. Then vigorous ascent ensues in cumuliform clouds. A crucial level in convective development is the level of free convection, LFC. Above this, a parcel is buoyant on its own. Also important is the convective condensation level, CCL, which is essentially the cloud base for convective clouds given surface humidity, similar to LCL. Pilots don't need to calculate these during flight, but an understanding of stability explains why certain days have fair weather cumulus versus towering cumulonimbus. Stable conditions, for example, under a strong inversion, result in smooth flying but possibly poor visibility, haze or fog trapped. Unstable conditions mean bumpy air and potential convective clouds. In summary, adiabatic cooling and heating govern cloud formation and vertical air motion. Rising air cools; if it cools to dew point, clouds form. Further lifting leads to latent heat release, possibly accelerating the rise if unstable. Sinking air warms and dries, dissipating clouds, as in high-pressure subsidence or on the lee side of mountains. Pilots observe these effects daily, for example when climbing through a haze layer at an inversion or when seeing puffy cumulus mark thermals that gliders might use. Cloud and fog overview. Clouds are visible masses of tiny water droplets or ice crystals suspended in the atmosphere. They form when air becomes saturated and water vapor condenses, or deposits, onto microscopic particles. Cloud types and their characteristics are key indicators of weather conditions and are important for pilots to recognize, for example, to anticipate turbulence, icing, or precipitation. Fog is essentially a cloud at ground level, posing a major hazard by reducing visibility. In this section, we discuss how clouds form and the classification of cloud types, then examine various forms of fog, mist, and haze that pilots must contend with. Cloud formation and description. Cloud formation fundamentally requires air to be cooled to its saturation point, dew point, so that water vapor can condense into liquid droplets or sublimate into ice crystals. The most common mechanism is cooling by upward movement of air. Adiabatic expansion, convective lifting, solar heating of the surface causes air parcels to rise, cooling as they expand. If they cool to the dew point, cumulus clouds appear at the condensation level. Orographic lifting, air forced up over mountains will cool and often form clouds on the windward side, cap clouds, orographic cloud. Frontal lifting, warmer air forced to rise over cooler air along weather fronts, especially a warm front, cools and forms stratiform clouds. Advection and turbulence, air mass moving over a cooler surface, like warm moist air flowing over cold ground or water, can cool from below and form a stratus deck. Turbulent mixing can also lift air in layers to saturation. In addition to lifting, clouds need condensation nuclei, tiny particles, dust, salt, smoke, on which water vapor can condense. In very clean air, humidity can exceed 100% slightly, supersaturation, before clouds form, but normally condensation starts just as RH reaches 100%. Clouds are classified by their appearance and altitude. Low clouds, bases from near the surface up to about 6,500 feet, 2,000 meters. Examples: stratus, a uniform gray layer that can bring drizzle or light rain; stratocumulus, low, gray, often in rolls or patches, often benign but can produce light showers; and nimbostratus, thick layered cloud producing steady rain or snow, often with very low bases. Fair weather cumulus, CU, are also low clouds with flat bases and cauliflower tops, indicating localized convection. They can grow into larger towering cumulus in unstable conditions. Middle clouds, bases roughly 6,500 to 20,000 feet, identified by the prefix alto. Altocumulus, AC, are mid-level patches or layers of rounded cloudlets, often a sign of mid-level instability or the remnants of decayed thunderstorms. Altostratus, is a gray or bluish sheet, thinner than stratus, through which the sunday may appear as a diffuse glow. It often precedes a warm front and can yield light precipitation. Nimbostratus can span low to mid-level, multi-level, during precipitation. High clouds, bases above about 20,000 feet, 6,000 meters. Composed mostly of ice crystals, identified by prefix 0. Cirrus, C, are thin, wispy fibrous clouds often seen in fair weather but can thicken ahead of a front or jet streak. Cirrostratus, Cs, is a thin, veil-like cloud layer that often produces a halo around the sun or moon, it frequently indicates a large-scale lifting. Cirrocumulus, CC, are small, white patches or ripples, not as common, and often transient. Clouds with vertical development, towering cumulus, TCU, and cumulonimbus, CB, span multiple levels. TCU are large cumulus with significant vertical extent, often appearing before thunderstorms form. Cumulonimbus are thunderstorm clouds, with bases typically in the low or mid-levels and tops often reaching high into the troposphere or even the lower stratosphere, anvils flattening out near the tropopause. CBS contain vigorous updrafts and downdrafts, heavy precipitation, lightning, sometimes hail, and severe turbulence. Pilots avoid cumulonimbus by a wide margin due to their multitude of hazards: turbulence, hail, icing, wind shear, tornado potential. Each cloud type gives clues. For instance, layered clouds, stratus, altostratus, usually indicate stable conditions with widespread lift and can bring continuous precipitation and poor visibility, but generally little turbulence. Convective clouds, cumulus, cumulonimbus, indicate instability and can bring showers or thunderstorms with turbulence. High-thin clouds, cirrus, may signal moisture aloft or the approach of a weather system. Fog, mist, haze. Fog is a cloud in contact with the ground, composed of tiny water droplets suspended in the air, reducing horizontal visibility to less than 1 kilometer. Mist is similar to fog but less dense, with visibility 1 to 5 kilometers, in UK aviation definition, between 1,000 meters and 5,000 meters. Both fog and mist form in very humid air when water vapor condenses into droplets. Haze is not formed by condensation of water but by fine dry particles. It reduces visibility especially in the distance, but typically does not feel humid. Haze often gives a grey or bluish veil in the air and can reduce visibility to a few kilometers, especially under high pressure with stable air. There are several types of fog, classified by their formation mechanism. Radiation fog forms on clear nights with calm winds, when the ground cools rapidly by emitting infrared radiation. The air in contact with the cooling ground is chilled to its dew point, causing fog to develop in situ. It typically occurs in low-lying areas or valleys towards dawn. Radiation fog is common in autumn and winter nights under high pressure. It can be shallow or quite dense, and often dissipates after sunrise as the ground warms, unless the sun is very weak. Light breeze can aid formation by mixing cool air upward, but strong wind will disrupt it. Advection fog occurs when moist air moves, advects, over a colder surface, cooling it to dew point. A classic example is a warm, humid air mass flowing over a cold ocean current or snow-covered ground. The air cools from below and fog forms. Advection fog can be thicker and more persistent than radiation fog, and it can occur day or night. Sea fog is a type of advection fog over oceans or coasts. Upslope, or orographic, fog, created when moist air is forced up terrain slopes and cools adiabatically. If it reaches dew point, a fog or cloud layer forms along the slope. This is essentially a stratus cloud on the hillside and can drift over passes or mountaintops, affecting airports at elevation. Frontal fog develops in the vicinity of fronts, usually warm fronts, where precipitation falls from warm air aloft into a colder layer near the surface. The rain can evaporate into the lower cold air, adding moisture and cooling it, evaporative cooling, saturating the air to form fog. This is common with warm fronts that produce extended rain. One often sees a zone of fog on the cold side of the front. Steam fog forms when cold air moves over warmer water. Water evaporates from the surface into the cold air, quickly saturating it and condensing into wispy fog just above the water. It often looks like steam rising. This is seen in autumn when cold air blows over warm lakes, or in Arctic regions as Arctic sea smoke when extremely cold air flows over relatively warmer open ocean. Steam fog is generally shallow but can be very dense directly over the water. Fog poses a serious hazard to aviation by reducing visibility to minima or below. It can disrupt airport operations, causing delays or diversions, and creates difficult conditions for takeoff and landing when instrument procedures are required. Pilots must pay attention to temperature dew point spreads, local geography, and forecasts. Haze and smoke, often grouped together as they both involve dry particles, also reduce visibility and can be widespread under stable high-pressure systems or downwind of large fires. Unlike fog, haze does not typically moisten aircraft surfaces or form droplets. However, it can significantly cut slant-range visibility on approach, especially when looking toward the sun. In haze, lights from a distance appear dim or with halos. In summary, for pilots, fog and mist are about moisture condensing in situ and tend to occur with high RH and light winds. Haze is about particles in dry air and often accompanies stagnant air masses. All reduce visibility and must be considered in flight planning and when determining approach minima. Proper meteorological information, META/TAF, will distinguish these: fog as FG when visibility less than 1,000 meters, mist as BR for 1,000 to 5,000 meters, and haze as Hertz in meta codes. Precipitation overview. Precipitation is water in liquid or solid form that falls from clouds to the Earth's surface. The development of precipitation in clouds is a key aspect of weather. Pilots need to understand how precipitation forms, because its type and intensity, rain, snow, hail, etc., affect visibility, aircraft performance, and can signal dangerous conditions like icing. In this section, we explain the processes by which precipitation particles grow in clouds and then outline the various types of precipitation and their characteristics. Development of precipitation. Not all clouds produce precipitation. Clouds consist of countless tiny droplets or ice crystals that are initially too small, microns in diameter, to fall out. They are kept aloft by slight air currents. For precipitation to occur, some of these particles must grow large enough, roughly greater than 0.2 millimeters, to overcome updrafts and fall as drizzle or rain, or snowflakes, etc. There are two primary mechanisms for growth of precipitation particles in clouds: collision coalescence, warm rain process. In warm clouds, larger water droplets form, perhaps by condensation on larger nuclei, and begin falling slightly faster than smaller ones. As they fall, they collide with and coalesce, merge, with smaller droplets, growing in size. This process is dominant in clouds with no ice. Given enough vertical depth and time, droplets can grow to raindrop size, 1 to 5 millimeters. If the cloud is too shallow or updrafts too weak, coalescence may only produce drizzle, very small drops. Collision efficiency is not 100%, but turbulence and differing fall speeds help droplets to meet. Eventually, drops become heavy enough to fall as rain. This process explains much of the precipitation in warm convective clouds, for example, tropical showers. Ice crystal process, Bergeron-Fintyson process, in colder clouds, mid-latitude clouds with parts below freezing, called mixed-phase clouds, precipitation often starts as ice. These clouds contain supercooled water droplets and ice crystals together. At a given sub-freezing temperature, the saturation vapor pressure over ice is lower than over liquid water. This means in a mixed cloud, the air can be saturated with respect to liquid but supersaturated with respect to ice. Water vapor thus preferentially deposits onto the ice crystals while the supercooled droplets lose vapor, evaporating slightly. The ice crystals grow at the expense of the liquid droplets. This is the Bergeron process in simplified terms. The growing ice crystals can become snowflakes. They might later fall through warmer air and melt into rain, or reach the surface as snow if temperatures remain below freezing. In addition to vapor deposition, ice particles and supercooled droplets can collide, riming, aggregation, to form graupel or larger snow aggregates. The outcome can be steady widespread precipitation, from stratiform clouds like nimbostratus, or showers, from cumuliform clouds, depending on cloud dynamics. These processes can operate together. For instance, in a large cumulonimbus, the upper parts use the ice crystal mechanism and the lower parts encourage collisional growth, This yields heavy rain and possibly hail.
Types of precipitation. Precipitation is categorized by phase and drop, or particle, size, structure. Drizzle, DZ, very fine droplets, diameter less than 0.5 millimeters, that appear to flow down slowly. Drizzle usually comes from low stratus clouds or fog, stratus or stratocumulus. It can significantly reduce visibility, especially when very fine. Light drizzle can be like mist. Rain, raw, liquid water drops larger than 0.5 millimeters. Rain intensity varies from light to heavy. It typically falls from nimbostratus, steady, prolonged rain, or cumulonimbus, towering cumulus, showery rain. Raindrops rarely exceed about 5 to 6 millimeters in diameter because larger ones break apart due to air resistance. Moderate to heavy rain can greatly reduce visibility and, if cold, can cause airframe icing if the aircraft skin is below 0 degrees Celsius. Freezing rain, drizzle, FZRA, FZDZ, rain or drizzle that falls as liquid but freezes upon contact with surfaces that are at or below 0 degrees Celsius. It occurs when a warm layer aloft melts snow into rain, but a shallow subfreezing layer near the surface is too thin to refreeze it before landing. The supercooled drops will instantly freeze on impact, forming a glaze of ice. Freezing rain is extremely hazardous for aircraft, severe icing, and for surface operations, glaze ice on runways. It is often associated with warm fronts in winter. Snow, SN, precipitation of ice crystals, most often in complex hexagonal form, snowflakes. Snow forms when the entire cloud and precipitation column are below freezing, allowing ice crystals to grow and aggregate. It can range from light snow with small flakes to heavy snowfall with large clumps of flakes. Snow reduces visibility, especially wet snow can be intense, and can accumulate on runways. For pilots, dry snow blowing can also cause drifting and reduced ground visibility. Snow grains and ice pellets. Snow grains are very small, flat or elongated opaque ice particles, like tiny grains of rice, that fall from stratus clouds, usually not in showers, more like drizzle but in frozen form. Ice pellets, sleet in some terminology, are transparent or translucent ice balls typically 1 to 5 millimeters diameter. Ice pellets often rebound off surfaces and make a tapping sound. They form when snowflakes partially or wholly melt in a warm layer then refreeze before hitting the ground. Ice pellets indicate a temperature inversion aloft, warm air over cold surface air. Hail, GR, frozen precipitation in form of balls or irregular lumps of ice, at least 5 millimeters in diameter. Smaller ones, less than 5 millimeters, may be called small hail or ice pellets if from convective clouds. Hail forms within strong convective clouds, cumulonimbus, with intense updrafts. Supercooled droplets freeze onto a nucleus, like a frozen raindrop or graupel, and multiple cycles up and down in the storm can add layers of ice until the hailstone becomes too heavy and falls out. Hailstones can range from pea-sized to golf ball, baseball size or larger in extreme storms. Hail poses a serious threat to aircraft, as it can dent or break windshields, damage leading edges, and even disable engines. Fortunately, hail is generally associated with severe thunderstorms that pilots avoid via radar and strategic deviation. Other forms include graupel, soft hail or snow pellets, usually 2 to 5 millimeters opaque white ice, forms by heavy rimming of snow in convective clouds, often seen in snow showers, and virga, precipitation that evaporates before reaching the ground, seen as trailing streaks below clouds. Virga can indicate microburst potential when from high-based thunderstorms. Each precipitation type is often tied to certain cloud types and weather situations. A pilot should infer likely precipitation from the type of clouds present or forecast, e.g., stratiform clouds yield steady rain or snow. Convective clouds yield showers or hail. A temperature profile near freezing might mean sleet or freezing rain. Understanding precipitation types helps in anticipating issues like icing, freezing or frozen precip, visibility, heavy rain, snow, and turbulence, often in convective precip. Air masses and fronts. Overview. The atmosphere can be divided into large volumes of air called air masses, which acquire particular temperature and humidity characteristics based on their source regions. When air masses move and meet, their boundaries are called fronts, which are often associated with significant weather changes. In this section, we describe the types of air masses and how they form and change, and then discuss fronts, the different kinds: warm, cold, occluded, stationary, and the typical weather each brings. Air masses. An air mass is a vast body of air, hundreds or thousands of kilometers across, with relatively uniform temperature and moisture in the horizontal direction. Air masses form when air remains over a region for enough time to acquire the characteristics of that surface, whether it be a warm tropical ocean or a cold continental interior. The classic air mass source regions are generally flat areas with homogeneous surfaces, like oceans, deserts, snowfields, and typically under high pressure, stagnant conditions so the air can stagnate and take on traits. Air masses are classified based on their temperature: tropical, polar, Arctic, Antarctic, and moisture, maritime or continental, tropical, T, originating in low latitudes, warm, hot; polar, P, originating in higher latitudes, cold; Arctic, A, or Antarctic, originating near the poles, extremely cold; maritime, M, forming over oceans, moist; continental, C, forming over land, dry. These combine into air mass types such as mount, maritime tropical, warm, moist air, e.g., air from subtropical oceans, which is warm and humid, brings thunderstorms or heavy rain if lifted; court, continental tropical, hot, dry air, e.g., air over deserts, can cause very hot conditions and usually clear skies due to dryness; MP, maritime polar, cool, moist air, e.g., North Atlantic air moving toward Europe, often brings cool weather with showers or steady rain, depending on stability; CP, continental polar, cold, dry air, e.g., winter air over Siberia or Canada, brings clear, cold conditions, but can pick up moisture and become unstable if it moves over warmer water, causing snow showers; CA, continental Arctic, frigid, extremely dry air from the far north or south in Antarctic, severe cold snaps when moving southward. Air masses modify as they travel away from their source. For instance, a CP air mass moving over a warmer ocean will warm from below and gather moisture, becoming more unstable, often creating cumulus and showers downwind of coasts. Conversely, an mount air mass moving over a cool land surface will cool and lose moisture, perhaps causing fog or low stratus, then drying. The boundaries of different air masses are fronts, but even without well-defined fronts, gradual transitions occur. Pilots experience air mass changes as shifts in temperature, humidity, and often visibility, e.g., a continental air mass might be clear but hazy. A maritime one might be more cloudy with better visibility after rain clears particulates. Knowing air mass types helps anticipate broad weather characteristics. For example, maritime tropical air in summer suggests hot, muggy weather with potential thunderstorms. Continental polar air in winter means clear skies but very low temperatures and strong surface high pressure. Fronts. A front is a transition zone between two air masses of different densities, usually due to temperature contrast, and also humidity contrast. Fronts are three-dimensional surfaces sloping away from the ground. The warmer air mass is always above the colder, denser air. They are classified by the motion of the air masses involved. Cold front. The leading edge of an advancing cold air mass, replacing warmer air. Typically, a cold front has a steeper slope, 150 on average. As the cold air wedges under the warm air, it forces the warm air to rise, often rapidly. Weather. Cold fronts often bring a narrow band of active weather, a line of showers or thunderstorms, sometimes squall lines, if the warm air is unstable, or a band of rain, snow if more stable. Ahead of a cold front, winds are often from a warmer direction, SW in mid-latitudes, and temperature is warm, pressure falls. As the front passes, temperature drops sharply, winds swing, often from SW to NW in NH, pressure rises, and visibility usually improves once any post-frontal showers clear out, as cooler, drier air moves in. Cloud sequence for a fast-moving cold front might simply be cumulonimbus and towering cumulus directly associated with the front, whereas a slower front can start with alto cumulus or alto stratus then lower to rain clouds. Warm front. The leading edge of an advancing warm air mass, gliding over a retreating cold air mass. Warm fronts move more slowly and have a gentler slope, 1 to 100 or 1 to 150. The warm air rises over the cold air in a broad ramp. Weather. Warm fronts typically produce extensive stratiform cloud layers and steady precipitation. The classic sequence approaching a warm front: high cirrus and cirrostratus, then altostratus, then thick nimbostratus with lowering stratus fractus clouds and fog. Precipitation, rain, freezing rain, sleet, or snow depending on temperatures, can occur for many hours ahead of the surface front. As the warm front passes, precipitation tapers off, temperatures rise, winds veer, in NH, usually from ESE ahead to SW after passage, and pressure stops falling. The air mass behind a warm front, the warm sector, is typically warmer but often humid and hazy with stratocumulus or fog. Occluded front, occlusion, forms when a cold front catches up to a warm front, lifting the warm air off the ground entirely. There are cold occlusions and warm occlusions, depending on the relative temperature of the air behind the cold front versus ahead of the warm front. In either case, the weather is a mix of both frontal types, widespread clouds and precipitation like a warm front, but also convective pockets like a cold front. An occlusion often produces persistent cloudiness and precipitation. The cloud sequence can be complex, but generally lots of nimbostratus and embedded cumulus. Occlusions are common in mature low-pressure systems. Stationary front. A front that is not moving, the air masses are in a standoff. Weather on a stationary front can resemble a prolonged, milder version of a warm front's weather on the warm side and clear cold conditions on the cold side, or it might just be a zone of cloudy, rainy weather that lingers. Winds tend to blow parallel to the front, keeping it in place. Stationary fronts can eventually dissipate or reactivate as cold or warm fronts if one air mass starts moving. When a front passes a given location, notable changes usually occur: temperature change, wind shift, pressure tendency change, and often a change in cloud and precipitation. Frontal weather can be hazardous to flight due to low ceilings, poor visibility, wind shifts, wind shear, icing, especially in cold and warm frontal precipitation zones, and convective turbulence in cold fronts. Pilots plan for these, e.g., avoiding strong cold fronts with thunderstorms, anticipating alternates if a warm front's low ceilings affect destination, etc. Finally, the life cycle of a mid-latitude depression, frontal low, involves fronts. A wave develops along a stationary front, creating a warm and cold front. The low deepens, wind circulates counterclockwise around the low in NH, with the cold front wrapping around, then an occlusion forms, and eventually the low fills and fronts weaken. This life cycle, sometimes called the Norwegian cyclone model, describes how frontal systems evolve. Understanding it helps a pilot interpret synoptic charts and predict how weather will change over a few days.
Pressure systems. Overview. Pressure systems are large-scale regions of high or low atmospheric pressure relative to the surroundings. They are fundamental drivers of weather patterns. High-pressure areas, anticyclones, generally bring stable, calmer weather, while low-pressure areas, depressions or cyclones, are associated with clouds and precipitation. In this section, we outline the principal pressure patterns on Earth, then discuss anticyclones in detail, non-frontal depressions, and the intense tropical revolving storms. The principal pressure areas. On a global scale, certain semi-permanent pressure belts exist due to global circulation, as mentioned earlier. For example, low pressure predominates near the equatorial region, the intertropical convergence zone, where warm air rises, and high pressure is typically found in the subtropics around 30 degrees latitude. The subtropical highs, such as the Azores High in the North Atlantic or the Hawaiian High in the Pacific. Around 50 to 60 degrees latitude, especially in the winter hemisphere, persistent subpolar low-pressure areas occur, like the Icelandic low or Aleutian low in the northern hemisphere. Polar regions generally have cold high pressure, especially over cold landmasses in winter, for example, the Siberian High. These principal pressure areas shift with seasons. The ITCZ moves north and south with the sun, subtropical highs strengthen in summer, etc. They form the broad climatic zones: equatorial trough, rising motion, convective rain, subtropical ridge, sinking air, arid zones, mid-latitude lows and highs, storm tracks between them, and polar highs. In mid-latitudes, traveling high and low pressure systems, migratory anticyclones and depressions, dominate day-to-day weather, steered generally eastward by the jet stream. Pilots see the effects of these systems in weather briefing charts, large H for highs and L for lows with attendant fronts. Anticyclone. An anticyclone is a high-pressure system, an area of higher pressure than its surroundings with air flowing outward, diverging from the center at the surface. In the northern hemisphere, surface winds around a high blow clockwise and slightly outward, counterclockwise in the southern hemisphere, due to Coriolis and friction. Anticyclones typically feature descending air, subsidence, in their core, which warms adiabatically as it sinks, leading to clearing and drying of the air. General properties of anticyclones: weather. High pressure usually brings fair weather, little or no precipitation, often light winds, especially near the center, and fewer clouds. Skies can be clear or only scattered, except perhaps some stratocumulus or fog in stagnant areas. In summer, highs often bring hot, dry weather. In winter, a high can bring cold, clear nights, with frost, but also the risk of fog or low stratus if moisture is present and winds are calm, due to radiative cooling and stable stratification. Types of highs. A warm anticyclone, like the subtropical high, has warm air aloft and generally warm air throughout. It's associated with large-scale subsidence under the descending branch of the Hadley cell, for example, Azores high. A cold anticyclone typically forms over very cold surfaces in winter, for example, Siberian high, where the air near the surface is frigid and dense. Cold highs can be very strong, for example, surface pressure 1040 to 1050 plus hPa, and bring clear, extremely cold weather. Their subsidence inversions can trap pollutants or fog in low levels, air quality issues. Ridges and wedges. An extension of a high-pressure area is called a ridge. On weather maps, a ridge is an elongated area of high pressure, often bringing similar fair weather along its axis. A wedge is essentially the same concept, sometimes used to describe a high extending between lows. Subsidence inversion. As air sinks in a high, especially from aloft where moisture was low, it often forms a temperature inversion aloft. Air warms as it descends, so a layer may become warmer than air below it. This caps convective clouds. Pilots might experience smooth flying under a high but with a persistent haze layer or stratocumulus trapped under the inversion. While generally benign for flying, lack of strong winds or storms, anticyclones require caution regarding fog, especially radiation fog in high-pressure nights, and potential low-level wind shear or inversion-related turbulence, usually mild. Also, thermals can be suppressed on stable high-pressure days, affecting glider operations. Non-frontal depressions. Not all low-pressure systems are associated with classic fronts. Non-frontal depressions are lows that form due to various localized processes rather than along major air mass boundaries. Some examples include thermal lows. These form due to intense surface heating, which causes air to rise and pressure to drop. They are common over hot land surfaces like deserts in summer, for example, the low over northwest India/Pakistan that helps drive the summer monsoon, or the heat low over the southwestern United States. Thermal lows are shallow and primarily driven by temperature, often not accompanied by fronts. They can cause local convergence and thunderstorms due to the intense heating. Orographic lows. Terrain can induce low pressure on the downwind side of mountains. For instance, as air crosses a mountain range, it may create a lee-side trough or low, sometimes called a lee cyclone. Examples: the Alpine lee low, Genoa low, south of the Alps under certain flow patterns, or a low east of the Rockies, Colorado low, when Pacific air spills over. These can generate significant local weather, strong winds, storms, even without a classic frontal structure initially, though they often eventually draw in fronts. Polar lows. These are small but intense low-pressure systems that occur in polar or subpolar maritime air masses, often in winter. A polar low is sometimes dubbed an Arctic hurricane, typically a compact, 100 to 500 kilometers across, storm that forms over open water poleward of the main polar front, usually under very cold upper-level conditions. They can produce strong winds and heavy snow in a small area. Polar lows are non-frontal in the sense that they don't form along the primary fronts, they are driven by instability, cold air over relatively warm water. Troughs of low pressure. A trough is an elongated area of low pressure. Some troughs are extensions of larger lows, frontal troughs, but in tropical or subtropical regions one can have troughs that are not accompanied by temperature fronts, for example, tropical waves or thermal troughs. Weather in a trough zone is often unsettled, rising motion, cloudiness, showers, despite the lack of a defined front. Non-frontal lows still bring bad weather. Rising motion means clouds and precipitation, potentially thunderstorms if unstable. They might not be as predictable as frontal cyclones and often smaller in scale, making them challenging to forecast and avoid. Pilots should treat any low-pressure area as a source of potentially adverse weather, be it poor visibility, precipitation, or turbulence, frontal or not. Tropical revolving storms. Tropical revolving storms are intense low-pressure systems that form over warm tropical oceans and rotate cyclonically, counterclockwise in NH, clockwise in SH. Depending on location, they are called hurricanes, Atlantic, Northeast Pacific, typhoons, Northwest Pacific, or simply tropical cyclones, Indian Ocean, Southwest Pacific. In general, a tropical cyclone is characterized by a warm core center, very steep pressure gradient, and strong winds spiraling around a calm eye. Key characteristics: formation. They typically form between about 5 degrees and 20 degrees latitude, not at the equator because Coriolis force is needed to initiate rotation, over oceans with sea surface temperatures of 26 to 27 degrees Celsius or higher. Conditions needed include a pre-existing disturbance or convergence area, like a tropical wave, adequate Coriolis force to impart spin, low vertical wind shear, so the storm structure can build vertically, and high humidity through a deep layer. When these conditions persist, clusters of thunderstorms can organize and heat release from condensation lowers surface pressure, drawing in more air, a positive feedback that can lead to a self-sustaining vortex. Structure. A fully developed tropical cyclone has a central eye, which is an area of relatively calm, clear conditions and the lowest pressure. Surrounding the eye is the eye wall, a ring of towering cumulonimbus with the most violent winds and heaviest rain. Around that are spiral rain bands, bands of thunderstorms spiraling into the center. These systems are typically 300 to 800 kilometers in diameter for the main cloud mass, though effects, like waves, some clouds, extend further. The vertical extent is enormous, convective clouds reaching 50,000 feet or more. Winds at the surface near the eye can exceed 100 knots in severe storms. The central pressure can be extremely low, for example, 900 to 950 hectopascals in a strong hurricane. They are warm core systems, meaning aloft the temperature in the eye is higher than environment due to the release of latent heat. Movement. Tropical cyclones generally drift westward and slightly poleward out of the tropics, steered by trade wind flow. As they reach subtropical latitudes, they often curve toward the poles and east, rightward in NH, leftward in SH, due to the influence of the mid-latitude westerlies. If they move over land or over cooler water, they weaken, losing their energy source of warm ocean heat and moisture. Many will eventually transition into extratropical storms or dissipate. Weather and hazards. The weather in a tropical cyclone is severe. The eye wall brings torrential rain, extreme winds, severe turbulence. Hail is uncommon because of warm maritime air, though possible, and frequent lightning is usually less than in mid-latitude storms but can still be present. The most hazardous aspect is the wind and turbulence. No aircraft except specially equipped reconnaissance planes would go near the core. Outside the core, rain bands can cause squalls and embedded thunderstorms. At altitude, convective tops can reach jet cruising levels, and widespread convective clouds make for an impassable barrier for aircraft. Additionally, tropical cyclones spawn strong low-level wind shear and occasionally tornadoes in outer rain bands. Flight operations. Pilots avoid tropical cyclones by a wide margin. Flight routes are replanned if a hurricane is forecast along the path. Airlines and general aviation alike must heed warnings. SIGMETs are issued for tropical cyclones. Airports can be closed due to strong winds well before the storm hits. The low pressure also affects altimeters. A significant pressure drop of, say, 50 hectopascals means altimeters would overread by 1,500 plus feet if not adjusted. Flying through or under a tropical cyclone is extremely dangerous. Aside from military hurricane hunters, it is essentially never done in civilian aviation. In summary, tropical revolving storms are the most intense low-pressure systems on Earth. They demonstrate how powerful atmospheric processes can become when fueled by warm oceans. Pilots must respect their destructive potential. Giving them a very wide berth is the only safe procedure. Climatology Overview. Climatology looks at prevailing weather patterns and climate zones over seasons and regions. While meteorology often focuses on short-term phenomena, understanding the typical climate in different parts of the world is important for flight planning and anticipating weather en routes or at destinations. In this section, we outline the major climatic zones of the world, highlight some features of tropical climate, like monsoons, describe common weather patterns in the mid-latitudes, and note some prominent local winds and their associated weather effects. Climatic zones. The Earth's climate is often divided by latitude and modified by continental versus maritime influence. Broad climatic zones include tropical zone, roughly between the tropics, about 23.5 degrees north to 23.5 degrees south. Characterized by high solar angle year-round, leading to warm or hot temperatures. Many areas have only subtle seasonal variation in temperature. Precipitation patterns define subzones. Equatorial regions, near 0 degrees, are typically wet year-round, rainforest climates, whereas just poleward of that, around 15 degrees minus 25 degrees, lie the subtropical deserts. High-pressure belts yield very low rainfall. The tropical zone includes monsoon regions, with distinct wet and dry seasons. See below. Temperate, mid-latitude, zone, roughly 30 degrees to 60 degrees latitude in both hemispheres. This zone has significant seasonal contrasts, warm/hot summers and cool/cold winters, especially pronounced over continents. Weather is highly variable due to frequent traveling pressure systems and fronts. Westerly winds dominate. Precipitation is moderate on average, distributed through the year but often with a slight preference for winter in Mediterranean climates, dry summer, wet winter, or summer in continental interiors, thunderstorm season. Polar zone, from roughly 60 degrees to the poles, especially beyond 66.5 degrees, the Arctic and Antarctic circles. Characterized by low sun angles, very cold winters, and short cool summers. Precipitation is generally light, often falling as snow. Polar regions have permanent ice or tundra climates. In aviation, polar atmospheres are often very stable, inversions, but can produce severe weather when polar air clashes with mid-latitude systems. Other ways to classify climate consider factors like humidity, for example, arid versus humid, and seasonal behavior, monsoonal, Mediterranean, etc. For pilots, knowing climate tells what weather to generally expect. For example, equatorial Africa will likely have daily thunderstorms, a desert region means dust or sand haze, rare rain, mid-latitude oceanic areas mean frequent low-pressure systems and changeable weather. Tropical climatology. Tropical climates are generally warm, little temperature variation through the year, but they can have strong precipitation patterns. Intertropical convergence zone, ITCZ. This is a near-equatorial belt of low pressure where the trade winds meet and air rises, creating a band of convective clouds and heavy precipitation. The ITCZ migrates with the seasonal sun, moving northward during the northern summer and southward in winter. Regions under the ITCZ experience frequent thunderstorms and heavy rain, especially in the afternoons or in pulses. Monsoons. A monsoon is a seasonal reversal of wind direction associated with differential heating of land and sea. The most famous is the South Asian monsoon. In summer, the Asian landmass heats up, drawing moist air from the Indian Ocean inland, southwest monsoon, which leads to a rainy season, torrential rains, widespread thunderstorms and low clouds over India, Southeast Asia. In winter, the land cools and high pressure over Siberia pushes dry air out, northeast monsoon, resulting in a dry season over those same regions. Other monsoon systems occur in West Africa. Summer onshore flow brings rain, winter offshore brings dry, and a weaker monsoon-like pattern in Australia. Monsoons are critical for their respective regions' weather. The wet season can bring flooding and challenging flying conditions, low visibility, thunderstorms, whereas the dry season can bring clear skies but possibly dust. For example, the Harmattan wind in West Africa is a dry, dusty northeasterly during the winter. Tropical cyclones, covered in detail earlier as tropical revolving storms, are a key part of tropical climatology. Some tropical regions have a defined cyclone season, for example, Atlantic hurricanes mostly June to November. Pilots must be mindful of these seasons when planning routes through tropical oceans. Trade wind climate, many tropical areas, like Caribbean islands, Hawaiian islands, etc., have trade winds blowing steadily from east or northeast. The windward sides of islands get frequent showers and upslope clouds, whereas the leeward sides are drier, rain shadow. This pattern is fairly steady, giving predictability to local flying conditions, for example, expecting turbulence or cloud on windward slopes, and clearer conditions leeward. In summary, tropical climatology involves a rhythm of wet and dry periods rather than large temperature swings. Flying in the tropics often means dealing with thunderstorms, heavy rain, and possibly cyclones in the wet season, and generally good weather but occasional fog or haze in the dry season, with high temperatures and possibly turbulence due to convective heating. Typical weather situations in the mid-latitudes, roughly 30 degrees - 60 degrees, experience a great variety of weather due to the constant interaction of cold polar air and warm tropical air, mediated by the jet stream and pressure systems. Some typical scenarios include westerly flow with migratory cyclones. This is the classic pattern for Europe, North America, and Southern Ocean latitudes. A series of depressions, low pressure systems, travel east or southeast, embedded in the prevailing westerly winds aloft. Each brings a sequence of weather. Ahead of the low, or its warm front, there may be milder air and stratiform rain, then the cold front passes with showers or squalls, followed by a cooler clear spell between systems. These Atlantic or Pacific lows can come every couple of days, a progressive pattern. Pilots in these conditions face regularly changing weather, alternating frontal cloud/precipitation and clearer interludes, with strong jet stream winds aloft. Blocking high, anticyclonic conditions. At times, a large, stationary high pressure can establish itself in mid-latitudes, deflecting the usual storm track. This can cause an extended period of stable weather. For example, a summer high might bring a heat wave and drought, or a winter high might bring cold, foggy conditions. While flying under a blocking high tends to be free of convective storms or heavy precipitation, the challenges include potential fog/low stratus, especially in winter in high pressure, haze buildup, and if near the periphery of the high, strong inversion-related wind shear. Local low-level jets and wind events. Mid-latitudes also see phenomena like nocturnal low-level jets, especially in central North America, which can cause wind shear at night, or strong downslope windstorms, for example, Chinook on the east side of Rockies, or Fawn in the Alps during certain synoptic setups, discussed below. These are tied to the larger patterns but create local hazards. In essence, mid-latitude weather is highly dynamic. Pilots must frequently consult synoptic charts, upper winds, and temperature forecasts because conditions can vary significantly day to day. The mid-latitudes are where frontal aviation weather is at its most complex, requiring good interpretation of weather briefings for safe flight. Local winds and associated weather. Certain regions of the world are known for pronounced local winds, which often arise from local topographical or thermal effects, but are embedded in the larger scale pattern. We have discussed land/sea breezes and mountain winds earlier. Here are some notable named local winds and their weather impacts. Fohn, already described. This warm, dry downslope wind, for example, in the Alps, can cause temperature jumps and clear weather on the lee side of mountains while bringing turbulence. Associated weather, clear skies or lenticular clouds above, low RH, potential for rapid snowmelt or drying. Mistral, a cold, strong north or northwesterly wind that funnels down the Rhône Valley to the Mediterranean, southern France. It occurs when high pressure lies over northwest Europe and low pressure over the Mediterranean. The Mistral can clear skies, bringing crisp visibility, but produces severe gusts, turbulence, and very choppy conditions over the sea near the Riviera. Pilots in affected areas plan for turbulence and strong headwinds or crosswinds on north-south runways. Bora, a violent cold northeasterly wind descending to the Adriatic coast from the Balkan Mountains. It occurs when cold air builds up on the inland side, for example, over winter snowfields, and then spills over to the coast under a pressure gradient. The Bora brings clear, cold weather but dangerously strong gusts, capable of exceeding 50 to 60 knots, and turbulent eddies. It can suddenly reduce visibility by kicking up sea spray or dust. Sirocco, a warm or hot south to southeast wind originating over the Sahara and blowing into the Mediterranean, particularly affecting Italy, Malta, etc. It typically occurs ahead of a low-pressure system approaching from the west, drawing up desert air. The Sirocco brings high temperatures, low visibility due to dust or sand, a reddish haze, and sometimes turns into a humid wind with low clouds or rain after crossing the sea. Aircraft may experience dust in the air, engine filters need consideration, and performance reduction due to heat. Monsoon winds, as noted, these are seasonal, but locally, during onset or retreat of monsoon, winds can shift dramatically, for example, sudden onset of moist onshore flow with towering clouds. The local weather goes from a hot, hazy dry season to an extended rainy period within days. Each local wind has a characteristic impact on weather, be it rapid drying, heating, cooling, or sudden high gusts. Pilots who operate in those regions become familiar with them. Often airports have specific procedures when such winds are forecast, like specific runways usage or weight restrictions. Knowledge of local winds is part of climatology because these winds recur in certain patterns every year or season. For example, a pilot planning a spring flight in the Alps should anticipate possible Fohn conditions. One flying to Nice in winter might check for Mistral warnings. Recognizing these names on weather forecasts or SIGMETs is important for readiness and safety. Flight hazards. Overview. Weather-related hazards pose significant risks to flight safety. Pilots must be able to recognize and avoid or mitigate these hazards through strategic planning and in-flight decisions. In this section, we summarize key meteorological hazards: airframe icing, turbulence, wind shear, thunderstorms, and their byproducts like lightning and hail, tornadoes, temperature inversions, special hazards of mountainous areas, phenomena that reduce visibility, and certain conditions encountered near the stratosphere. Each of these can jeopardize flight operations if not properly managed. Icing. Aircraft icing occurs when supercooled water droplets in clouds or precipitation freeze upon contact with the aircraft's surfaces, or when the aircraft surface is at or below 0 degrees Celsius and moisture deposits, frost. Icing is most likely in visible moisture and at temperatures between about 0 degrees Celsius and -20 degrees Celsius. Colder than -40 degrees Celsius clouds are mostly ice crystals which usually don't stick. There are several types: rime ice, opaque, milky ice that forms from small supercooled droplets freezing quickly on impact. It has a rough, crystalline texture. Rime typically occurs in stratiform clouds or the upper fringes of convective clouds at temperatures around -10 to -20 degrees Celsius. It builds a irregular shape that disrupts airflow but is relatively brittle and can be shed easier. Clear ice, glaze, transparent or glossy ice from larger droplets that spread out before freezing. It forms in cumuliform clouds, with strong updrafts, or freezing rain. Temperatures just below 0 to -10 degrees Celsius often produce clear ice. Clear ice is denser, sticks firmly, and can form a smooth heavy coating that significantly alters airfoil shape. It is especially dangerous due to its weight and ability to form far back on wing surfaces, even beyond de-icing boot coverage. Mixed ice, a combination of clear and rime ice, common in many cloud conditions, giving a rough but also extensive buildup. It can form when temperature and droplet sizes vary in a cloud layer. Frost, while not due to flight in clouds, frost is ice that can form on an aircraft on the ground by deposition. A thin layer of frost on wings before takeoff is very dangerous as it spoils lift. Regulations require all frost to be removed before departure. Hazards of icing. Ice accretion on wings and tail reduces lift and can cause stalls at higher airspeeds and angles than normal. By altering the airfoil and adding weight, increases drag dramatically and can also interfere with propeller and engine inlets, reducing thrust. Icing can immobilize control surfaces or trim devices, for example, antennas, flap rails accumulating ice, and it can clog pitot or static ports, leading to instrument failures. Propeller aircraft may get ice on propeller blades and induction icing in the engine, carburetor icing even in clear air around +5 degrees Celsius with humidity, or intake icing in turboprops/jets due to freezing mist. Icing on windshields or canopy reduces visibility. Severe icing can quickly become catastrophic. Many aircraft have a limited tolerance, icing certification in moderate icing only. Avoidance and mitigation. Pilots should avoid areas of known severe icing. Pre-flight, this means examining forecasts. In flight, one should escape icing conditions by climbing or descending to warmer air, above 0 degrees Celsius, or to very cold levels where clouds contain only ice crystals, if aircraft and performance allow. Most large aircraft and many smaller ones have anti-icing or de-icing systems, heated wings and props, pneumatic boots, heated pitot/static, engine anti-ice. These systems can handle light to moderate icing but can be overwhelmed by severe icing or freezing rain, hence avoidance is key. If caught in unexpected icing, pilots should act promptly, engage de-icing, change altitude to find a layer without icing, and declare an emergency if needed. Even ground icing, frost/snow on aircraft, must be dealt with via de-icing fluids before takeoff. In summary, icing remains one of the great weather threats, insidious because it can build gradually or suddenly, and deadly because it directly impairs the aircraft's ability to fly.
Turbulence. Turbulence, as discussed earlier, is chaotic, disturbed airflow that can buffet the aircraft. From a hazard perspective, turbulence can range from light, a slight bumpiness, to extreme, violent motions causing loss of control or structural damage. Principal concerns for pilots are loss of control or structural stress. In severe turbulence, momentary loss of control or large bank altitude excursions can occur. The aircraft structure can be overstressed if flying too fast. That's why pilots slow to VA, maneuvering speed, in very rough air. At or below that speed, the aircraft will stall, which is preferable, before structural failure. Passenger and crew safety. Injuries can occur if occupants are not belted in during unexpected turbulence. Sudden clear air turbulence has caused serious injuries when people hit the ceiling. Secure loose items and keeping seatbelts fastened even when seated is a standard recommendation. Instrument performance. In extreme turbulence, attitude or altitude hold autopilot modes may struggle or disconnect. Pilot workload increases. Also, pitted static instruments can momentarily misread if the turbulence causes unusual angles of airflow into sensors, though modern systems handle this well. Engine effects. For example, in turbulence inside thunderstorms, water, hail ingestion or airflow disruption can flame out engines, though this is typically a risk within convective storms rather than clear air turbulence. Operationally, turbulence is managed by avoidance when possible, detouring around storm cells, or known mountain wave regions, etc., and by adhering to turbulence penetration procedures, slowing down, securing cabin, minimizing unnecessary maneuvers. Pilots also communicate turbulence reports, PIREPs, so others in dispatch can adjust altitude or route. Wind shear. Wind shear is a sudden change in wind speed and/or direction over a short distance, vertically or horizontally. It is especially hazardous during takeoff and landing, when the aircraft is at low altitude, relatively low speed, and close to stalling speed margins. A wind shear can abruptly reduce the headwind component, or increase a tailwind, causing a loss of lift and airspeed, effectively a sudden drop of performance which can lead to a hard landing or crash if not corrected immediately. Common sources of dangerous wind shear: microburst, downbursts. These are intense, localized downdrafts from thunderstorms that spread out at the surface in all directions. They create a shear pattern, first an increasing headwind, if approaching the storm, then a strong downdraft, then a sharp transition to tailwind as the aircraft flies through the microburst cell. The total effect is a severe loss of lift and airspeed on the backside of the microburst. Microburst wind shear near the ground has caused accidents, e.g., wind shear induced by a thunderstorm on final approach. Microburst can occur even with little rain reaching ground, dry microburst. Frontal shear. A fast-moving cold front or squall line can have a sharp wind shift line. If an aircraft takes off or lands as the front is passing, the surface wind can change direction and speed markedly in minutes. Similarly, a sea breeze front on a hot day can create a sudden wind shear boundary. Low-level jet and inversions. At night, an inversion can form a few hundred meters above ground with a strong low-level jet, a region of fast wind, above cooler calm surface air. On takeoff climb, an aircraft may suddenly encounter much stronger winds aloft, which is a shear. After takeoff, it might translate to a performance gain, a sudden headwind, giving extra airspeed, but turning crosswind or descending back through it can be challenging. Wind shear at an inversion is common in early morning hours. Terrain-induced shear. Near hills or buildings, wind can vary significantly. For example, on approach over a ridgeline to a valley airport, winds might drop or shift when descending below the ridge due to the sheltering effect, or rotor zones. Also, large buildings or hangars near runways can cause swirling or uneven wind. Recognition and mitigation. Modern airports, especially those with a history of wind shear, are equipped with low-level wind shear alert systems, LLWAS, or terminal Doppler weather radar to detect microburst and shear. Pilots are trained in wind shear recovery techniques. Basically, if a shear is encountered, e.g., an airspeed and lift loss, apply maximum power and pitch up to stick shaker if necessary, to climb away or at least minimize descent until out of the shear. Takeoff and landing performance calculations also account for known wind shear by adding margins or avoiding operations when shear is reported. A stable approach policy helps if the approach becomes unstable due to shear, indicated by sudden deviations in airspeed or glide path. A go-around is prudent. Flying through known severe wind shear is to be avoided. That includes not taking off or landing in the face of a thunderstorm overhead. Awareness of wind shear reports, PIREPs, ATIS mentioning wind shear, or thunderstorm proximity, is crucial. Thunderstorms. Thunderstorms, cumulonimbus clouds, are among the most dangerous weather phenomena for aircraft. They encapsulate multiple hazards, severe turbulence, inside and around a thunderstorm, especially in the updrafts, downdrafts, and at cloud edges, like the shear between updraft and surrounding air. Turbulence can be extreme. This can toss an aircraft around violently. Even 20 nautical miles away downwind, one can encounter turbulence from a storm, due to gravity waves or residual turbulence. Hail. Thunderstorms, particularly strong ones, generate hail in their cores. Hailstones can be large, several centimeters. They are often thrown out of the cloud by strong winds and can fall outside the visible cloud, sometimes in clear air under an anvil. Hail can severely damage an aircraft's windshield, leading edges, and engine fan blades. A single encounter with large hail has downed aircraft or forced emergency landings due to damage. Lightning. A lightning strike can puncture the aircraft skin, damage electronics, or temporarily blind pilots. Modern airliners are built to withstand lightning by conducting it through the skin with minimal damage, but strikes can still cause system upsets or minor damage, like pitting. Lightning is most frequent in the mature stage of a thunderstorm. It can strike aircraft even in apparently weak storms or in cloud areas that don't seem very electrified. While rarely catastrophic, lightning is certainly a hazard to avoid. Heavy precipitation. Intense rain can cause engine flameouts, as large quantities of water quench combustion. Though engines are certified to ingest a lot of water, extreme conditions in a thunderstorm core can exceed that. Heavy rain on the windshield can dramatically reduce visibility and also refract light such that visual cues are lost. Combined with turbulence, it can disorient pilots. On the ground, wet runways with wind shear can be deadly, hydroplaning risk. Microburst and wind shear. As mentioned, thunderstorms can produce powerful downdrafts that spread out and create wind shear. This is particularly deadly if it strikes an aircraft near the ground. Tornadoes. In the most severe thunderstorms, supercells, or even in organized squall lines, tornadoes or funnel clouds can form, discussed separately below. They are obviously catastrophic to encounter. Icing. The strong updraft regions of a thunderstorm contain abundant supercooled water, causing extremely rapid ice buildup on airframes if entered. It can overwhelm anti-ice systems quickly. Also, some storms have a layer of supercooled droplets above the freezing level, leading to clear ice on airframes that pass under the anvil or through the cloud edges. Static electricity, street. Elmo's fire. Thunderstorms and intense precipitation can cause static buildup on the airframe, leading to corona discharges, St. Elmo's fire, on windshields or nose, a visual sign of intense charged air, often preceding a lightning strike. It's more of a warning sign than a hazard itself, but it indicates you're in a dangerous electrical environment. Avoidance. The primary defense against thunderstorms is avoidance. Pilots use weather radar, storm scopes, and strategic route planning to keep well clear. Flying under a thunderstorm, below the base, is extremely dangerous due to downdrafts and hail, and flying above is not usually possible for big systems. Tops can reach 50,000 feet plus. Even if over, you risk severe turbulence at the anvil top. The general rule is to circumnavigate by a large margin, at least 20 nautical miles from severe cells, more if possible, especially downwind side where hail can fall. At night or in instrument conditions, reliance on radar is key. One must be proficient in interpreting it, e.g., understanding that a radar shadow could mean intense core with hail. Air traffic control may provide vectors around known weather, but the ultimate responsibility lies with the pilot to refuse a clearance that penetrates a cell. On the ground, if thunderstorms are at an airfield, operations may pause. Winds can shift or gust suddenly, and microburst can occur. Pilots will typically hold or divert rather than attempt an approach in the midst of a thunderstorm overhead. In summary, a thunderstorm is a complex hazard, essentially all the worst weather hazards packaged together. Modern aviation treats them with utmost respect. Avoid them whenever possible. Tornadoes. Tornado is a violently rotating column of air pendant from a cumulonimbus cloud, in contact with the ground. It is the most intense small-scale wind event on Earth, with wind speeds that can exceed 200 knots in the strongest tornadoes. Funnel clouds or waterspouts are similar phenomena. A waterspout is a tornado over water. Tornadoes often form from supercell thunderstorms, in their mesocyclone region, or from severe squall lines. Weaker ones, landspouts, can form from smaller storms. For aviation, a tornado means certain disaster if encountered in flight. The structural stress of winds that change by hundreds of knots across a few meters is far beyond any aircraft's design. Fortunately, tornadoes are narrow, tends to a few hundred meters wide usually, and visible, funnel, debris cloud, if not rain-wrapped. The key is to avoid being anywhere near a parent thunderstorm that can produce one. This is usually accomplished by the general thunderstorm avoidance techniques already described. Pilots should heed tornado watches, warnings as indicators of severe storm potential. At airports, if a tornado is observed or strongly indicated by radar, standard procedure is to evacuate the tarmac and seek shelter. Aircraft in the air would divert or hold far away. If airborne near a storm that spawns a tornado, giving it an extremely wide berth is the only safe action, far more than the 20 nanometers recommended for general storms, since debris can be thrown far and inflow winds extend outward. In short, tornadoes are an extreme hazard but one that is inherently tied to thunderstorms. Avoiding the storm avoids the tornado threat. There is no pilot action that can overcome a direct tornado encounter, so avoidance is absolute. Inversions. An inversion is a layer of the atmosphere in which temperature increases with height, the opposite of the normal decrease with height in the troposphere. Inversions act as stable caps on vertical motion and have several implications. Wind shear. Often, especially at night, a radiation inversion forms near the ground, cool air trapped below warmer air. Wind above the inversion might be significantly stronger than near the surface, since friction slows the lower air, but above the smooth cool layer winds can race freely. This can create a shear zone at the inversion top. As mentioned, an aircraft climbing or descending through such an inversion can experience a sudden change in wind speed, direction. Turbulence. Typically, air below an inversion is very stable, smooth flying. However, turbulence can occur at the boundary if strong winds above induce shear, creating eddies. Also, mechanical turbulence from below can be trapped under the inversion, making for a choppy layer just below it. Visibility and weather. Inversions often trap pollutants and moisture beneath them. Fog, stratus, haze, or smog often persist under an inversion, with clear air above. For example, a marine inversion can keep a low stratus deck over an airport that won't clear until the inversion breaks. Similarly, in winter high pressure, a surface inversion overnight can trap mist and smoke, causing very poor visibility and freezing fog, while just a few hundred feet up it might be clear. Performance impact. If a strong low-level inversion exists and an aircraft climbs into warmer air above, for instance, a winter morning with cold air at surface and a warm layer aloft due subsidence, the reduction in air density in the warm layer can reduce climb performance temporarily. Also, the engine might suffer a slight power reduction in the warmer, less dense air aloft. Operationally, pilots should note forecast inversions. For instance, if an approach is coming in over water at night, sea surface cooler, into warmer coastal air, a low-level inversion can cause a shear. Likewise, during takeoff, an inversion can make windsock readings near ground misleading if strong winds exist just 500 feet up. Awareness allows compensation, e.g., higher approach speed if expecting shear, or avoidance of heavy takeoff if climb performance might be marginal in a warm layer. Inversions themselves are not dangerous in the way storms are, but their side effects, wind shear and visibility reduction, must be managed. Hazards in mountainous areas. Mountain flying introduces numerous weather-related hazards, many of which we touched upon: mountain waves, katabatic winds, etc. But to summarize, turbulence and wind shear. Mountains disturb airflow. Strong winds meeting a ridge create turbulent eddies and rotors on the lee side. Even on the windward side, updrafts and abrupt terrain can cause localized turbulence, mechanical. When winds aloft are strong, over about 20 to 30 knots, expect turbulence near ridges and in valleys. Low-level wind shear is common as winds are channeled and change direction around terrain. Mountain waves. These can produce severe up and down drafts far downwind, lee waves. An aircraft may encounter an area of strong lift followed by sinking air that exceeds its climb capability. This is extremely dangerous if near terrain, a downdraft forcing you down towards a ridge. Pilots crossing mountains in strong winds often aim to cross well above ridge level and be prepared for turbulence and altitude fluctuations. Clouds and visibility. Orographic cloud can form rapidly when moist air ascends terrain. A clear valley can fog in quickly, or a pass can become obscured by cloud. Mountain obscuration is a serious risk for VFR pilots. Even IFR, drifting in cloud near terrain, is hazardous without proper altimeter settings and terrain clearance. In winter, heavy snow showers can occur on windward slopes, drastically reducing visibility, while lee slopes might be clear and deceptively inviting. One must remember the weather can change when moving across a ridge. Icing. In mountainous areas, clouds, especially stratiform cloud banks hugging terrain or wave clouds, may be full of supercooled droplets. Also, orographic lift can extend cloud layers to higher altitude than typical for a given region, meaning you might stay in icing conditions for longer when climbing. Ice can accumulate faster due to high liquid water content in orographic clouds. Furthermore, ice may form on one side of the aircraft more than the other if one wingtip is closer to moist updraft near a ridge. Altimeter error. As noted, strong winds and low pressure pockets on the lee side of mountains can cause local pressure anomalies. If flying from the windward to leeward side at the same indicated altitude, you might be closer to terrain than you think because the pressure on the lee side is lower, altimeter overheads. Pilots need extra clearance margin or updated altimeter settings when crossing ranges. Density altitude. Many mountain airports are at high elevation. On warm days, the density altitude can be extremely high, thin air, reducing engine power and lift. Coupled with terrain, no room to climb gradually, this is a performance hazard. High field elevation plus temperature must be considered, e.g., taking off from a 7,000 feet elevation valley at plus 30 degrees Celsius is a serious challenge. Mountain thunderstorms. Terrain can trigger convective storms in summer afternoons. These storms can be anchored to peaks and produce sudden flash floods or downdrafts in valleys. They may not move much, but sitting over a peak they throw lightning and hail around the area. Pilots should avoid flying near thunderstorms in mountains because escape routes are limited by terrain. Safe mountain flying involves thorough weather planning, checking winds aloft, stability, for wave potential, freezing levels, etc. Often flights are done in early morning when winds are calmer and convective activity minimal. Pilots crossing mountains will use ridge lift and avoid downdraft areas if in small planes, or in airliners will ensure they have ample altitude above the terrain. Special training in mountain flying emphasizes these points. Visibility reducing phenomena. Low visibility can be as dangerous as any other hazard, leading to disorientation or inability to see obstacles, runway. Many visibility hazards are weather-related. Fog and mist. Already covered, fog, visibility less than 1,000 meters, can ground aircraft due to below minimum conditions. Rapidly forming fog, like radiation fog around dawn, can trap aircraft at airports. Mist, slightly better vis, still poses challenges. These require instrument approach capability or diversions. Fog can also appear in flight unexpectedly if flying from warm into cooler areas, like coastal fog banks. Haze. Dry particles, dust, pollution, can reduce visibility to a few kilometers even under otherwise clear skies. Haze is common in high-pressure areas and can be exacerbated by pollution, urban, industrial smog. It's particularly troublesome for VFR pilots, losing sight of terrain or other aircraft. Even IFR flights need sufficient visibility at minima to land, and haze can sometimes be dense enough to affect that. Smoke. Wildfires or agricultural burning can create widespread smoke layers. Smoke behaves like haze, but can be more dense and with a strong smell. It can reduce visibility to near zero in extreme cases, flying through a thick smoke plume. Smoke also can affect engine air quality, particulate ingestion, and occasionally even cockpit air quality, smell, eye irritation. Pilots treat heavy smoke similar to fog in terms of avoidance or instrument flight. Dust and sandstorms. In arid regions, strong winds can lift dust or sand into the air, creating dust storms, or haboobs, that advance like walls with visibility near zero in their core. These can be associated with thunderstorm outflows or strong pressure gradients. Sand and dust can not only eliminate external visual references but also erode moving parts, pitted tubes, engine compressors. Flying into a sandstorm is extremely hazardous. IFR capability doesn't help if the air itself clogs intakes and abrades surfaces. Ideally, one lands before such a storm arrives or diverts around it. Even after it passes, runways might be covered in sand, and fine dust might linger at altitude. Blowing snow. In cold regions, loose snow can be picked up by wind, causing whiteout conditions. Blowing snow behaves like dust in the air, and if combined with snowfall, can make IFR approaches very difficult. Few visual cues, diffuse horizon. Whiteout is a phenomenon where sky and snow-covered ground blend into one, removing contrast. Pilots can lose all sense of height above ground. This is a critical hazard for VFR operations in polar or winter conditions. Volcanic ash. While not weather, it's geological. Ash clouds from volcanic eruptions are included in meteorological warnings because they drift with the wind. Volcanic ash is extremely abrasive and can cause jet engines to flame out by accumulating and melting into glass inside. Ash is often not visible at night or on weather radar. Special advisories, VA SIGMETs, warn pilots of ash clouds. The safe procedure is absolute avoidance, detour or stay grounded if an ash plume is over the route. Encounters have led to engine failures and serious damage. Precipitation effects. Heavy rain or snow was mentioned. Beyond their direct effect, they reduce slant range visibility. Flying through heavy rain at night can be almost as bad as fog visibility-wise. Snow. Especially wet snow at night can create a strobe-like effect under landing lights, impacting pilot perception, the snow shower whiteout. Drizzle with fog also severely reduces runway visual range. Mitigation for low visibility includes having instrument approach capability, using onboard technologies, ILS, GPS approaches, autoland for Category 3 conditions, or delaying flight until visibility improves. Pilots and ATC also rely on accurate RVR, runway visual range, reports to make decisions. When encountering reduced visibility en route, like unexpected haze or smoke, IFR flight and careful navigation become crucial. If not qualified or if conditions deteriorate beyond capability, diversion or turning back is the safe option.
Stratospheric conditions. Modern jet aircraft often fly near the tropopause, around 30 to 40,000 feet, and occasionally enter the lower stratosphere when cruising at optimal altitudes or in climb. The stratosphere has unique conditions, temperature and performance. In the lower stratosphere, temperature stops decreasing with height and eventually increases. The standard tropopause temperature is about -56 degrees Celsius. Such extreme cold can impact aircraft operations. Fuel can approach its freezing point on long flights. Pilots monitor fuel temperature, especially on polar routes where cruise might be long at -65 degrees Celsius ambient. If fuel gets too cold, a descent to warmer air is required. Engine performance in very cold air is generally good, denser air for a given altitude, but as one goes higher into stratosphere, increasing temperature and decreasing density can reach limits, the coffin corner where high-speed Mach buffet and low-speed stall margins converge. Lack of weather. The stratosphere is typically free of clouds, except anvil tops of storms that occasionally overshoot. No convective turbulence originates there, and no significant weather systems. They are tropospheric phenomena. This means flight in the stratosphere is usually smooth and above any storms. However, one must be cautious when near the tropopause. Just below might be the tops of thunderstorms or jet stream-related turbulence. Crossing the tropopause region can come with phenomena like clear air turbulence associated with jet streams or tropopause folds. Radiation and ozone. At high altitudes, exposure to cosmic radiation is higher. On a single flight, this is not an acute hazard, but over a career, pilots, especially on polar and high-altitude routes, accumulate non-trivial radiation doses. Another factor is ozone concentration, which is greater in the lower stratosphere. Aircraft draw air for cabin pressurization from the outside, and if not filtered, high ozone can cause irritation. Modern jets often have catalytic converters to reduce ozone in the cabin air. Pressurization and oxygen. The stratospheric ambient pressure is very low, at 40,000 feet, about 1/5 sea level pressure. Aircraft cabins are pressurized, usually to the equivalent of 6,000 to 8,000 feet. In an unlikely event of decompression at such altitudes, humans would lose useful consciousness in seconds without supplemental oxygen. Thus, stratospheric flight demands reliable pressurization and quick don masks for crew as a backup. This is not a weather hazard per se, but an environmental reality of high-altitude flight. Engine operation. The combination of cold temperatures and low densities means engine flameouts can occur due to transient issues like ingesting ice crystals. In recent years, a phenomenon called ice crystal icing has caused engine power loss events when flying near deep convection anvils, even at high altitude, as tiny ice crystals ingested can melt and refreeze in compressors. Pilots now avoid evident anvil cirrus outflow regions to mitigate this. Miscellaneous. When Concorde used to fly in the stratosphere, 60,000 feet, it encountered the stratopause warming, which actually helped it. While we don't have supersonic airliners now, it's worth noting that above the tropopause weather remains mostly quiescent up to mesospheric phenomena, like noctilucent clouds at very high altitude or polar stratospheric clouds, which matter for ozone chemistry. For subsonic jets, the main concerns are the cold, radiation, and ensuring to avoid the remnants of tropospheric weather, like the turbulence of a nearby jet streak. In summary, the stratosphere is generally an ally to aviation, smooth and clear, but it poses its own extremes, cold and thin air. It reminds us that as we leave the weather below, we enter an environment where human physiology and some aircraft systems are pushed to their limits. Pilots respect these conditions by careful monitoring of temperatures, pressurization systems, and potential high-altitude turbulence. Meteorological information overview. To make informed decisions, pilots rely on a wide array of meteorological information. This includes real-time observations, various types of weather charts and forecasts, and specialized reports and warnings. Meteorological services around the world gather and disseminate this data continuously. In this section, we outline the main sources of weather information for aviation, observational data, the common weather charts used, the information pilots use in flight planning, and the organizations and systems behind these services. Observation. Accurate observations form the foundation of weather information. Surface observations, at aerodromes, regular reports called meteorological aerodrome reports, are issued, typically hourly, with special reports, species, when conditions change significantly. A meter provides current weather at the station, wind, direction/speed, visibility, runway visual range of low, present weather, rain, fog, etc., cloud cover and height, temperature/dew point, and altimeter pressure, QNH. Meters are given in a coded but standardized format globally. ATIS, Automatic Terminal Information Service, broadcasts provide pilots with a current meter and other relevant airport info continuously by radio. Automatic weather stations, AWOS, may generate meters at smaller airfields. Upper air observations, weather balloons, radiosondes, are released globally, usually 2 times daily, to measure temperature, humidity, pressure, and winds aloft. These create soundings that meteorologists use to assess stability and wind profiles. For pilots, the data feeds into upper wind and temperature forecasts and helps predict cloud tops or icing layers. Increasingly, aircraft themselves provide observations. Many airliners automatically transmit data on winds and temperatures during flight, via AMDAR systems, which improves real-time analysis. Weather radar, ground-based weather radars, often Doppler radars, detect precipitation. They provide near real-time imagery of rain intensity and storm structure. Meteorological services use radar to monitor thunderstorms, frontal rain bands, etc. Pilots don't typically access raw ground radar during flight, they have onboard radar, but pre-flight they might look at national radar summaries to see areas of convective weather. Satellite observations, geostationary and polar orbiting satellites continuously image the Earth's atmosphere in visible and infrared. Satellite images show cloud cover, development of systems, and features like hurricane eyes or jet stream cirrus. Infrared imagery indicates cloud top temperatures, and thus approximate height. These are crucial for areas with sparse surface data, for example, over oceans. Pilots may see satellite image loops as part of pre-flight briefings for big picture awareness, for example, a gathering cyclone or extent of monsoon clouds. Pilot reports, PREP/AirUp. Pilots in flight sometimes report significant weather they encounter, such as turbulence, icing, cloud tops, etc. These reports are relayed and help others. For example, a PREP of severe turbulence at FL 340 over a certain waypoint will warn other aircraft. Automated AirUps, from ADC or cars, also disseminate conditions. Voluntary pilot reporting remains a key source for phenomena like wind shear or mountain wave turbulence that might not be otherwise observed. Together, these observations feed into the continuous meteorological picture. Aviation weather information always references current observations, for example, the latest meter for destination, or PREPs along a route, because forecasts rely on and are updated by observational truth. Weather charts. Weather charts distill observations and model forecasts into graphical form. Surface analysis chart. This shows the distribution of sea level pressure with isobars, and identifies high and low pressure centers, fronts, warm, cold, occluded, stationary, and often troughs or ridges. It is a snapshot of the current synoptic situation, or an analysis for a recent time. Pilots use it to see the big picture, where the pressure systems are and how they might affect winds and weather. For instance, one can identify a deep low, likely strong winds and fronts, or a sprawling high, fair weather. Pressure prognosis, forecast, charts, similar to analysis, but for future times, for example, plus 24 hours, plus 48 hours. They show predicted positions of highs, lows, and fronts. These help in flight planning beyond the immediate term. For example, a pilot planning a long flight might see that in 18 hours a cold front will pass their destination. Significant weather, SIGWICS, charts, these are specialized high-level or mid-level charts for specific flight level ranges, like low-level SWC for below FL 100 or high-level for FL 250-630, that highlight important en route weather phenomena. They include features like jet stream winds, with wind speed maxima, turbulence areas, for example, CAT or mountain wave regions, thunderstorm areas or lines, tropical cyclones, volcanic ash clouds, squall lines, and fronts with their altitudes. High-level SIGWICS charts, for example, show jet streams with wind speeds and tropopause heights, symbols for CB clouds, with tops indicated, areas of moderate or severe turbulence or icing. These charts are essential for flight planning at cruise altitudes. An airline dispatcher will use them to chart a path avoiding forecast turbulence or storm clusters. Wind/temperature aloft charts, these may be in map form or as data grids. For instance, a chart might depict wind barbs and temperatures at specific pressure levels, for example, 300 hectopascals FL 300 across a region. There are also prognostic charts for specific flight levels at intervals, or, nowadays more commonly, computer-generated wind/temp forecasts for any point. Pilots/dispatchers get wind and temperature forecasts along the route, either via tables or graphical vertical cross-sections, to compute ground speeds, fuel burn, and to choose the best altitude. Modern flight management systems can take gridded wind forecasts from the World Area Forecast System and optimize routings. Other charts, these might include precipitation forecast charts, convective outlook charts, where thunderstorms are likely, upper air stability indices, etc., depending on the region and briefing system. In Europe, for general aviation, gamut area forecasts or low-level significant weather charts provide information on regional en route weather below a certain altitude, cloud bases/tops, freezing level, etc. In mountainous regions, special charts might highlight valley fog or mountain passes forecast. A volcanic ash advisory chart is issued by volcanic ash advisory centers showing the forecast dispersion of ash clouds at specific flight levels. Weather charts condense a great deal of information into an accessible format. Pilots are trained to interpret these symbols and patterns. For example, tight isobars around a low on a surface chart means strong winds. A jet stream arrow on a high-level chart indicates potential CAT near it. A shaded region with CB symbols on a SIGWICS means embedded thunderstorms to be avoided. Information for flight planning. Before flight, pilots and flight dispatchers collect all relevant weather information. Aerodrome forecasts, TAF. A terminal aerodrome forecast is a prediction for weather at a specific airport, typically covering a 9 to 30-hour period depending on the airport. It's encoded format and includes forecast times for wind, visibility, significant weather, rain, snow, etc., clouds, with heights, and any wind shear or tempo changes. The TAF is essential for determining if conditions will be within landing minima at ETA or if alternates are needed. It might say, for example, becoming IFR in fog overnight or temporarily heavy rain with gusty winds from 1517 En route forecasts and wind data. These include wind and temperature forecasts at cruise altitudes, often provided in a flight plan package per waypoint or as a grid along the route. They also include significant en route weather like jet streams, turbulence, etc., often derived from the SIGWICS charts. Dispatch calculates fuel and routing based on expected winds, taking advantage of tailwinds or avoiding strong headwinds. SIGMETs and AirMAs, these are in-flight weather advisories. SIGMET, significant meteorological information, warns of serious hazards like active thunderstorms, convective SIGMET, tropical cyclones, severe turbulence, severe icing, volcanic ash, dust storms, etc., that could affect safety. They are issued regionally with validity times. Pilots check SIGMETs along the route for things like OBSC TGTSY within area. Severe icing FL 100 180 or sequel TS, squall line thunderstorms, moving east. AirMA is similar but for moderate hazards, often aimed at general aviation, for example, moderate mountain obscuration or moderate turbulence. In many jurisdictions, AirMAs cover lower-level phenomena not reaching SIGMET criteria. Gamut area forecast, Low-level forecasts. In Europe, a gamut is a plain language area forecast for low-level flights, giving conditions below a certain altitude, cloud, weather, this by geographic zones. In the US, there are graphical forecasts for aviation, GFA. Glider pilots and VFR pilots rely on these for non-TAF covered areas. NOTAMs, weather-related. While NOTAMs are for all operational info, some weather-related items like bird migration warnings, runway friction after snow, or lighting outages, affecting approach in low vis, are communicated via NOTAM and considered in planning. Specialized briefings. On longer oceanic flights, planners consult tropical weather advisories if near hurricane-prone regions, for example, NHC Outlook, upper wind/temperature charts from WAFC, icing probability charts, etc., as needed. Also, volcanic ash signets if any along the route, and space weather advisories for things like solar radiation storms that could affect communications on polar routes. During the flight, crews update their picture via VOLMET broadcasts, continuous HF/VHF broadcasts of meters and TAFs for major airports, data link weather, ACARS can request meter/TAF, and listening to ATIS of destination/alternates as they get in range. If conditions have worsened, they have contingency plans, holding or diverting. In summary, flight planning uses a comprehensive set of forecasts to ensure the flight can be conducted safely, from departure weather to en route winds, en route hazards, destination/alternate weather, and more. Meteorological services. Aviation meteorology is supported by a global network of services coordinated by ICAO and the World Meteorological Organization. Key aspects include national meteorological services. Most countries have an official meteorological authority responsible for providing aviation weather within their airspace. They operate weather offices at major airports and meteorological watch offices, MWO, for flight information regions. These offices issue meters, TAFs, SIGMETs, and other warnings for their area. World Area Forecast System, WAFS. This is a global system that provides standardized upper-level wind, temperature, and significant weather forecasts for aviation worldwide. There are 2 World Area Forecast Centers, WAFC, one in London, UK Met Office, and one in Washington, US NOAA, which run global forecast models and produce products like global wind/temperature grids and high-level SIGWIX prognostic charts. Airlines and aviation authorities receive this data, often via satellite or internet, to use in flight planning. The WAFCs back each other up to ensure continuous availability. Volcanic Ash Advisory Centers, VAAC, specialized centers, 9 globally, that monitor volcanoes and issue ash dispersion advisories and graphics. For example, London VIC covers Iceland and the Atlantic, Darwin VIC covers much of SE, Asia/Australia, etc. They coordinate with MWOs to ensure SIGMETs where ash are issued and that airlines are aware. Tropical Cyclone Advisory Centers, TCAC, similar approach for hurricanes/typhoons, specialized centers, often collocated with regional Met offices, provide info on cyclone tracks and intensities to support SIGMETs and flight planning. Aerodrome Meteorological Offices. At major airports, meteorological personnel or automated systems provide updated observations and sometimes on-site briefings or consultation for flight crews and ATC. For example, a dispatcher can call the meteorologist to discuss an unusual weather scenario, or ATC can get a warning about wind shear detected by Doppler radar. Meteorological broadcasts and data systems. Many countries have dedicated frequencies or systems, like VOLMET or ATIS, and digital data links, like ATIS via DATIS, or text weather via ACARS, to get weather to pilots. On long flights, airlines may send en route updates via SATCOM. Pilots also sometimes use modern electronic flight bags, tablets, to download weather mid-flight if internet connectivity is available, for example, via satellite Wi-Fi. Ultimately, these services aim to provide timely, accurate weather information to flight crews and planners 24/7. International standards, ICAO Annex 3, govern formats and dissemination so that a pilot can read a meter or SIGMET in any country and understand it. Meteorology is a team player in aviation. Forecasters work closely with air traffic management during significant events, like organizing flow management if a hurricane closes an airport, or convective storms require rerouting of flows.
By effectively using meteorological information from pre-flight briefing to landing, pilots can avoid the worst weather and mitigate the effects of unavoidable weather, thus ensuring safety and efficiency in flight operations. Conclusion: meteorology is not just an academic requirement but a vital practical skill set for any professional pilot. As we have seen, the atmosphere can present serene, favorable conditions one moment and life-threatening hazards the next. A deep understanding of meteorology enables pilots and flight dispatchers to anticipate and interpret the weather, to read the skies and weather charts and make sound decisions based on that knowledge. From the pre-flight planning stage, where route and altitudes are optimized to avoid headwinds or storm systems, to in-flight adjustments, such as detouring around convective buildups or handling an unexpected low-level wind shear, knowledge of weather is a constant compass for decision-making. By mastering the theory of meteorology, the behavior of the atmosphere, the genesis of winds and storms, the characteristics of clouds, and the interpretation of forecasts and observations, pilots can operate aircraft with greater safety and efficiency. They know how to avoid the worst weather, and equally important, they know what to expect if they must fly through challenging conditions, and how to mitigate the risks. This contributes directly to flight safety. Many aviation incidents and accidents have been avoided by pilots heeding weather warnings or cleverly circumnavigating hazards, while historically, lack of weather awareness led to tragedy. In summary, meteorology is a cornerstone of a pilot's expertise. It connects the theoretical knowledge of the atmosphere with real-world flying. A solid grasp of meteorological principles and diligent use of weather information allow flight crews to respect the power of nature while harnessing it, choosing efficient routes with tailwinds, planning safe altitudes above turbulence, timing departures to avoid fog, and always having Plan B for diversions. The ultimate goal is the safety of flight, and meteorology is an indispensable tool to achieve it. A pilot who is well versed in meteorology contributes significantly to the overall safety and success of every flight.